We can start the second day of this workshop. We start with the presentation of Alberto on the schools, followed by the one by Stefania. Please, Alberto.
Thank you very much. I would like to say just a couple of words to complement what Gabriele told us yesterday about the GGI. As you know, the GGI activities have two pillars. One, which is the organization of extended workshops, and one dedicated to the organization of schools for PhD students. And I will talk about this second part. As we heard yesterday, GGI started its activities in 2006 as a center to host long-term workshops. And in those years, typically we had 3 workshops starting from, let's say, mid-March, the first one, and ending at the end of October, early November. So during the winter months, from November till March, the GGI was not used. And actually, this is not completely correct because in 2008, a group of colleagues had the idea of organizing a school for PhD students on string and field theory. This school was called LACES, which is a nice acronym that stands for the Italian words of Advanced Lectures on Field and String Theory. And as they wrote, when they announced this school, LACES will help students to interact in a stimulating environment among themselves and with active scientists. And in addition, it provides a solid and more specialized background in theoretical physics to get a grasp of literature, to benefit from conferences and advanced international schools, and last but not least, to carry on successful research during the short period of their graduate studies. So that was the spirit of this first school organized at the GGI in 2008. The school was held at the end of November, early December, not only because in that period the GGI was available, but also because the school was mainly supported with the leftover residual money, which obviously becomes known and available only towards the end of the year. The school attracted, because also of these budget constraints, a limited number of students, mainly from the neighboring Italian universities, and the lectures were delivered by the organizers. So it was a sort of an in-house organization. But the school was highly appreciated and continued in the following years, more or less with the same format. So when I started my first term as chair of the theory division of INFN, almost 15 years ago, I thought that this example of LACES could be replicated. And the available months, the winter months of January, February, and early March, could be used to have schools based on the example of LACES. So I started to discuss with colleagues and friends in very different areas. And after a while, we came up with a proposal of having 4 schools in different topics of theoretical physics. LACES, dedicated towards string and field theory, a school on standard model and beyond standard model physics, so particle phenomenology, a school dedicated to statistical mechanics, statistical field theories, integrable models, and that sort of subject, and also a school on hadronic and nuclear physics, These topics enlarged very much the scope of the activities of the GGI at that time. Each of the schools had its own organizing committee. They were totally independent in their choices, and the only constraint that we gave was that the lectures had to be given at the blackboard, and the schools had to be very pedagogical, because we didn't want to replicate schools, international schools, where the lectures are given with slides and they are more of a review of subjects. They were supposed to be really formative schools. I should say that a big help came from the Science Foundation, which in 2014 awarded the GGI with a generous grant, which we called Simons at the GGI, which allowed us to support not only long-term visits associated to the workshops, but also to support lecturers and students for the schools. So these schools started their activities in 2014, and I should say that they were quite successful. This is a graph that tells you the number of students. This was LACES up to 2014. Then in 2014, the new schools with some ups and downs, but quite soon, the number of students reached the maximum capacity of GGI. Since we wanted to maintain a pedagogical and formative character for the schools, clearly the number of students could not exceed the maximum capacity of GGI. And the organizers of the various schools, unfortunately, had to reject a large number of applications. And this trend luckily remained also after the breakdown due to the COVID pandemic. So that was the status of schools, but in 2019 we thought that a fifth school could be organized and could take place here at the GGI, dedicated to another important area of theoretical research in INFN, astroparticle cosmology and gravity. And in the last few years, a different kind of school also started. It's a theory meets experiments, in which we bring together students from different communities, and this school, which is shorter than the others, is dedicated to a specific subject that is chosen every year. I think that the schools are quite successful. The atmosphere is very nice. There are a lot of students. There are a lot of interactions with teachers. Some of you have been lecturers at the schools. Here I see Costas that was lecturing a few years ago. And so I think this was the status in those years. And as Nando Ferroni told us yesterday, this was the basis to make a further jump, a further step forward. And indeed, in 2016, 10 years ago, on the anniversary of GGI, Nando and the executive board at that time came with the proposal to transform the GGI from an activity inside the theory division of INFN into a more structured into a structure of INFN, a center, a national center for advanced studies. So these activities on schools is going on and keeps attracting a lot of interest. And to mark the birth of the National Center for Advanced Studies, we had the idea of establishing an award dedicated to Galileo. So we started the tradition of the Galileo Galilei medal, a medal which is assigned every second year to one or more scientists who in the 25 years before the award have given important contributions in the areas of theoretical physics of interest to INFN. And the first award was the medal to Juan Mandacina. This was the motivation. Gabriele was the chair of the selection committee at that time. And then in 2021, we had the second medal to Alessandra Bonanno, Thibaut Damour, and Franz Pretorius for their work behind the discovery of theoretical work behind the discovery of gravitational waves. In 2023, we had the medal to Zwieberg, Lance Dixon, and David Kosover for the development of powerful methods and calculations in quantum field theory. And last year, a medal to Lenny Susskind and Pierre Sikibi for their work led to unveil connections between the largest and the smallest scales of nature. And next year, on February the 15th, the anniversary of Galileo's birthday, there will be the announcement of the 5th Galileo medal. So I think that as a community, all of us are very proud of what has been done here at the GGI, of what is doing, what will be done in the future. And I would like to take this opportunity to really thank all the people who made all this possible. First of all, the president of INFN at the time, Nando Ferroni, and the executive board for their support, in particular Antonio Masiero and Fabio Zwirner, with whom we nicely interacted during the transition time. To Gabriele for his constant help and advice to make the transitions smooth. I should say that at the beginning, these activities about schools was not so an easy task because some colleagues were a little bit skeptical. They were afraid that the GGI will lose its main mission. But as it turned out, the schools filled the gap and did not interfere at all with the workshops. So not only the establishment, but also the directors of GGI who came after me, Daniele Dominici, with whom I nicely collaborated during the transition time and in the month afterwards, Stefania, is she there? Because she had really to face difficult times during the lockdown and in the pandemic and the recovery. So thanks very much for maintaining the GGI in good health. And obviously Fulvio is the current director. Needless to say that a big thank also to the administrative staff, Mirella, Mauro, Annalisa, Alessio, and all the people who really make all this enterprise possible every day. So thank you very much. I think it's fair to say, in conclusion, that the GGI is a successful activity. We are very proud of what has been done and what is done currently. But of course, there is room for improvement. And new challenges are in front of us. So I think that really we should say happy birthday to the GGI and best wishes for the future. So thank you very much.
Thank you, Alberto, for this nice introduction. We can move to Stefania.
Good morning. Good morning, everyone. The title is Something More. That's because in 20 years of activity of the GGI, as you already know, we run 60 extended workshops, 67 schools, but also something more, and I will tell you what is more. I will follow the time, in this half an hour talk, I will follow the timeline and start from the lockdown, because when I was director, at the beginning of my directorship, we had to close. We had to close, and that was not easy. And we make any effort to transform the activities of the GGI from in-person activities to online ones, and that was, everything was really new. So I want just to sketch some of them, because I think it was an important step. First of all, we had to move Cortona. Cortona is the annual theory meeting also dedicated to the young people. My first talk was in Cortona after my degree. So we decided to fully devote to young researchers the Cortona edition in 2020 and 2021. Torino was supposed to organize, and some of the people who have to organize Cortona Young is here, Anna, Maria Luisa, Domenico also. And we got so many applications for Cortona Young, 150, that we decided to introduce also the video posters and also to attribute awards for the best web seminar and the best video poster. So I think we try to continue for the young people, and that was really important. Another thing that was organized during the pandemic are a series of web seminars called the GGIT breaks. The argument was covered a wide spectrum of argument in the theory of fundamental interactions, and also for this I want to really thank the organizing committee, Roberto Contino, Guido D'Amico, Francesco Deramo, Valentina Forini, David Marzocca, all these people, Domenico Orlando, Alessandro Sfondini, Andrea Tesi, Riccardo Torre, and Trincherini, all these people helped me in organizing 40 seminars given by the world's leading experts. And I could say that the GGIT break seminar were followed with great interest and participation by the theoretical community and became a weekly event every Wednesday at 5 p.m. Just a few examples. This is Naturalness and the Future of High Energy Physics by Gian Giudice and Riccardo Rattazzi. This is Reflections on 50+ years of success stories by Gabriele Veneziano. And this was a special event on Steven Weinberg and his legacy. We saturated soon our 1,000 accesses on the Zoom license with 4 seminars, the first one by Riccardo Barbieri, and then Witten and the others. So in general, the GGIT breaks have thousands of visualization on YouTube, and so this is an archive of great value. Another thing that was born during the pandemic was in the 2021, the GGI started a research fellowship program dedicated to very young researchers in theoretical physics to give them the opportunity to boost their career and to contribute to the GGI activities. And since then, 22 postdoc fellows got a 1-year grant. Their work has been scientifically stimulating, and that is reflected in their publications, seminars, and the career following the GGI fellowships. Some examples. Claudio Bonanno, who was Booth Fellow in 2021, received the Wilson Award in 2025, one of the most important international honors in the field of lattice field theory. William Jarret was Booth Fellows in 2022. Now he's a postdoc at the University of Hawaii, and he will be back at the GGI as organizer of a workshop next July. So I think we are doing a good job, and every year in December we have a GGI postdoc day to give room to the GGI postdoc activity. On September 21 in 2021, we had the first edition of the Women in Theoretical Physics Award Ceremony. This is a INFN National Prize for the best master thesis in theoretical physics, and to encourage the presence of women researchers in this area, and it is dedicated to Milla Baldacciolin, who was the first woman to hold a full professorship at the University of Padua. The award ceremony is held every year here at GGI. To date, 45 young scientists have been honored, and they are now carrying forward their research as PhD students or postdoc around the world. I want to mention that in this first edition, we also have the very first staging live of the play, The Hidden Force, Women in Physics and History, and that would go on to travel far and wide, finding extraordinary success. This play was conceived and curated by Anna Ceresole and the others that you can read there, and it offers a view of the physics of the 20th century through the eyes of four scientists, Vera Rubin, Marietta Blau, Madame Wu, and Milla Baldacciolin. So this was a beautiful way to honor the very first laureates of the INFN National Prize dedicated to Milla Baldacciolin. Okay. Theory meets experiment is the new school introduced in the 2023. Alberto already mentioned. So we add a new school, which is now 2 weeks, so has the same length of the other ones. And it aims of providing lectures covering basic topics from theoretical as well as experimental point of view on hot topic in the physics of fundamental interactions, which is suitable for a synergic approach joining theory and experiments. The first one in 2023 on the high-intensity frontier of particle physics, then in 2024 on neutrinoless double beta decay, and last November on direct detection across dark matter. We had very positive exit reports by organizers, speakers, and students, so we go on. This is an outreach program which was run from 2022 and 2024. The name is Grasping the Cosmos. It is an art and science project which is part of the regional research, development, and innovation project of the Tuscany region, promoted by the GGI and the museum system of the University of Florence. Sorry. It was curated by Valeria D'Ambrosio, an art historian and contemporary art curator, and by the physicist and science communicator Pietro Centorino. And Grasping the Cosmos was developed in 3 phases, 2 of them with an artist in residence during the editions of the 2023 and 2024 of the GGI School on Astroparticle Physics, Cosmology and Gravitation. Here you see the artist Daniela De Paulis during a presentation of her work at the school. Grasping the Cosmos was a cultural program fostering dialogue between art and science, designing collective and co-creative events. Here you cannot read the program, but we had a lot of events, educational activities, and outreach activities. You see, these activities were held at Villa Galileo. This is a picture taken during the inauguration of the exhibition In a Word's Outer Spaces by Daniela De Paulis. This is a guided tour to the exhibition. If you are curious, you can visit the site where all the videos, all the materials of this project is collected. Okay, I'm quite at the end. Alberto already mentioned that the GGI has been awarded by the Simons Foundation grant to institutes. This was the first grant, but what is very special that this grant has been given another time. So it has been awarded 2 times. And the second grant, it is for a 3-year period, and it is now going on. The program is Simon Visiting Program at the GGI, and it covers 4 different types of collaboration with GGI activities: long-term visits, participation to the workshops, participation of researchers and students from institutions with limited funding, and also short-term visiting research teams program. Also, we opened a partnership with the Pollica Physics Center, a recently established institute which organizes theoretical and mathematical physics workshops. So we are growing up, and also our connections are in a much more larger direction. I'm at the end. As Fulvio tell us at the beginning, 10 years ago, Antonio Garbasso, who was the director of the Institute of Physics of the Royal University of Florence, the name of this building is Antonio Garbasso, presented a paper by a 25-year-old Enrico Fermi entitled On the Quantization of the Perfect Monatomic Gas for publication in the Proceedings of the Accademia Nazionale dei Lincei. This work proved to be fundamental in many fields of physics, as it is well described by this recent paper by Roberto Casalbuoni and Daniele Dominici, From Florence to Fermions, a historical reconstruction of the origins of Fermi statistics 100 years later. This is the historical picture of Enrico Fermi, Nello Carrara, Franco Rasetti, and Rita Brunetti here in the cloister, okay, around the well. And as I often do, I show similar pictures taken during workshop and schools of participants of the activities of the GGI. So the GGI is really keeping the spirit of Arceti alive, and I wish it will do more in the next 20 years. Thank you.
Thank you, Stefania, and thank you again to Alberto and Stefania, not only for these presentations, but in particular for their work, continuous work in shaping, in founding and shaping the GGI as it is now, an international center. Now we can continue with the scientific part with Marco Cirelli, with an update on dark matter and prospects.
Okay, so thank you very much. Yeah, so my task here is, thank you very much for the invitation and for having me here. And I think that my task here is indeed to give a sort of overview of the status of the searches and a little bit of the theory, but it will be quite superficial, as you will see. Mostly the searches for dark matter about 2026, so the year we are now. And so I suggested this title to the director, The WIMPs and Beyond the WIMPs. And another alternative title could have been Dark Matter, Where Are You? Okay, in the sense that it's about 100 years that we know that dark matter exists in the cosmos, since Zwicky and 31 or 32, when he first detected that in clusters, but still we don't have an answer for this question. Or actually yes, because as an exclusivity for this audience, right today I have an answer for you, and the answer is that it's sitting somewhere on this plane. Okay, so it's only 90 orders of magnitude, and we know that dark matter is a sort of corpuscle. I don't want to say particle, but something that has the characteristic of matter, which in cosmology basically means that it dilutes as the inverse of the volume. That's the definition of matter in cosmology. So we know that some kind of matter exists over this range of 90 orders of magnitude, and it plays the role of the dark matter that we see in the cosmos. We don't know much more than that. So my task will be, in some sense, to jump up and down in this range of possibilities and highlight a few of the possible candidates. I'm not saying anything new, I'm just giving a sort of perspective of where we are right now. So there are some benchmarks on this plane. The first one is the lower bound. Okay, so we know that dark matter cannot be lighter than about 10 to the minus 21 electron volts, and that's because you don't want dark matter to have a de Broglie wavelength which is wider, larger than the smallest bodies inhabited by dark matter that we know, and those are dwarf galaxies. So you take a dwarf galaxy which has a size of about 1 kiloparsec, and you have a determination of the lightest mass that you can set inside that body, and it's about 10 to the minus 21 electron volts. At the other end of the spectrum, similarly, we take a dwarf galaxy, which has a mass of about 10 to the 4 solar masses or so, give or take an order of magnitude, and you obviously say that dark matter cannot be a particle or a body bigger than that, otherwise it wouldn't fit in such a body. So these two robust things are mostly dictated by the galaxy size, the dwarf galaxy size or the mass, and they are certainly guiding, so restricting to only 90 orders of magnitude the range of possibilities. Then there are a few benchmarks around this range here, which are not so important, but let me just mention them. The first one is the Planck scale, meaning that above this, we most likely think that dark matter is a composite object of some sort, and below this, it could be simply an elementary particle or an elementary body of some sort. Then you have another benchmark around here, around an electron volt, where you say that lighter than this, it's better to describe it as classical fields, like think of axions or axion-like particles. And above this, it can be essentially described as a particle, elementary or composite. And then a more conspicuous one, if you want, is a benchmark around the fraction of a kilo electron volt, around here, which tells you that dark matter must be bosonic if it's below this benchmark, or bosonic or fermionic if it's above this benchmark. This is simply because you can define a sort of effective occupational number of dark matter particles, defined as the density of a typical body, the density of dark matter in a typical astrophysical body like the galaxy today, divided by the typical intrinsic density of a dark matter particle, so its mass divided by its de Broglie volume, say. And if this number, if the mass is small enough that this number is much larger than 1, then it must be bosons, otherwise you cannot pack too many of them in the astrophysical system, such as the galaxy or other bodies. Okay? But other than that, all the range is open for grabs, and essentially you can fit candidates all over the place. So let me start right in the middle, and right in the middle means, of course, the weak scale, so the weak scale interactions, and of course, I'm talking about WIMPs. So WIMPs are one of the candidates, if not the most popular candidate of the past decades, and rightly so, in the sense that weakly interacting massive particles are very good, very well motivated, a very well motivated possibility. So this is, in my opinion, for two reasons. On one side, because you have two theoretical, let's say, pillars, which are the thermal freeze-out mechanism and the opportunity of having new physics at the TV scale, which I will discuss in a second. You all know about it very well. So this is the first big motivation for WIMP. And the other, say, motivation in some sense along the road for WIMPs is that the history tells us that the historical conjuncture is such that we can test them in 3 different ways, which are very promising in the different aspects. Okay, so let me first give you a word about the thermal freeze-out that you know very well, just to make a point later contrasting this and this. So thermal freeze-out means, I'm sure you know, that if I want to compute the dark matter density, the density of a certain species, let me call it chi here, as a function of the history of the universe, so as a time that goes on or temperature that goes down, you have this famous plot here that tells you that at the beginning the particles were in thermal equilibrium with the soup of the universe, and so you have as many chi's as any other species of the standard model, thanks to destruction, annihilation, and recreation of chi particles. So thermal equilibrium, everything is 1 in some proportions. Then at some point, as the universe expands and cools down, you have that the energy at disposal to create chi particles, which are typically heavy, so weak interacting masses, becomes no more available, and so the abundance of this species goes down following a typical Boltzmann suppression of this sort. And then, at some point, even the annihilations of chi particles into standard model species stops, freezes out, essentially because the universe expands so fast and the particles are so dilute that they don't find each other to annihilate anymore, and so you have that the density freezes at some point here. So this is the very well-known paradigm of freeze-out of dark matter particles, and it's encapsulated by this famous formula that tells you that if you want to reproduce the abundance of dark matter particles, chi particles, as a fraction of the total density in the universe, what you have is a simple formula that tells you that this is inversely proportional to the annihilation cross-section with a constant above here, which is of the order of 6 × 10⁻27 centimeter cube per second. So if you want to reproduce 26% of the abundance of dark matter in the universe, you need simply this magical thermal cross-section, cosmological cross-section, which is 3 × 10⁻26 centimeter cube per second. And it turns out that if you compute a typical weak interaction cross-section, so plugging in weak interaction strength and typical weak masses of the order of, say, 1 TeV, what you get is precisely the omega dark matter that you need. So the so-called famous WIMP miracle, meaning that WIMPs are automatically produced in the right abundance if you throw them in the soup of the early universe. You don't need to do anything. They have the right interaction to stop annihilating precisely when it's needed, right? So this is the fascination of the thermal freeze-out. And the point that I want to make is probably obvious to everyone here, but I think in the field it's not so well taken, is that these 2 pillars, let's say, are completely independent. So the fact that you have a thermal freeze-out fascination that produces dark matter in the right abundance is independent from the fact that new physics at the TeV scale should exist or not. So in other words, the fact that we haven't found the dark matter, supersymmetry, or whatever at the LHC doesn't mean that WIMPs are over, right? Okay, so this is probably obvious, but it's still worth saying, because sometimes there is a confusion between WIMPs, neutralinos, and other kinds of candidates of this sort. So to me, WIMPs remain still appealing because of this main pillar here, and because of the fact that we can test them in different ways with strategies that are very much complementary in collider, in direct detection, and in indirect detection. So let me start briefly with the status of direct searches, which probably you know very well. So this is the idea that we wait for one of the dark matter particles to hit a nucleus in an underground detector and give it a recoil that we can detect. So the current status of which, I'm going to use very much this summary that we published a couple of years ago with these authors. So this is the status of last year. There was a little bit of improvements, but we haven't pushed the V3 yet. So the idea is that this is the standard plane of dark matter mass and scattering cross-section over a nucleon in one of your experiments. And you see all these different constraints that are reaching more or less are going to reach very soon what is the neutrino background inside which it will be difficult to dig. So the space of parameters has been explored a lot, but still there are these slivers of empty space which have to be explored. What does theory says about this? Well, the theory, the basic simple ideas. Simple ideas is that if dark matter interacts really weakly through the exchange of a Z boson, then this is excluded by since decades. It would be somewhere here. See, if it interacts in a wider sense as a weaker particle that interacts through the Higgs, for instance, or exchanging a scalar at 3 level, it would be here, and so it would also be excluded since several years. But purely weakly interacting particles, such as, for instance, with one-loop interactions of this sort, interacting through W bosons, predict a cross-section which is loop-suppressed, and so somewhere here. And so they are still a good candidate which can be detected soon, maybe with the next generation of experiments. And we have examples of particles sitting somewhere there. So in the next few slides, I'm going to highlight some frontiers of, personal opinion, and of course one of the frontiers that people are exploring is this one, so pushing down and going towards even more weakly interacting particles. Okay, so that sort of concludes for direct detection. What about indirect detection? So indirect detection is another thing which is very, very active in this moment, and essentially means two things. The first one is charged cosmic rays. So the basic idea is that you have dark matter particles in the galactic halo or in other astrophysical environments. These dark matter particles annihilate and produce charged particles such as antiprotons, positrons, and other particles of this sort. So these particles go around in the galactic field, in the galactic magnetic field, so they spiral around, they lose by synchrotron radiation and other processes. They can be blown away by the galactic wind of stars that produces cosmic rays throwing the particles away. They can cross the galactic disk and so suffer shocks on the stars, on the interstellar gas and so on and so forth. And then some of them will reach the heliosphere, so the environment of the sun, and we can detect them with, say, AMS or CALET or DAMPE or the other experiments currently in orbit when they enter the sphere of influence of the sun. So we're going to see that on this, essentially right now, there are no excesses, there are no anomalous features, and so we can impose limits based on the non-detection of excesses of, say, positrons or antiprotons from the galactic environment. Another complementary strategy is looking for photons, of course, which means that in the same process of annihilation, you have the production of photons through different channels, and you can point your telescopes towards regions where you think that dark matter is densest, for instance, the galactic center, and see if you see an excess of photons, which you cannot explain through normal, say, astrophysics. So this is the only thing, I would say, which is still hotly debated, because there is an excess coming precisely from the galactic center, which is there since almost 20 years, detected by the Fermi satellite. So I'm sure you've heard about the GeV excess from Fermi at the galactic center. One way of illustrating this is to use this official data from the Fermi collaboration, and so it's the following. What you're looking at here are photon counts, so the number of photons collected by the experiment, in some binning, so 1 to 2 GeV, 2 to 10 GeV. So let's focus on this one in the center, so the binning in between 2 and 10 GeV of energy. So these are actually photon counts of detected photons, subtracting all the astrophysical models that we have. So including everything we know about astrophysics, okay? So you do all your predictions for emissions from astrophysical sources, and you subtract them from the data, and you get the residuals. So in the upper line, you have the residuals if you don't include anything exotic. And in the lower line, you have the residuals if you include a distribution of dark matter, so a contribution from dark matter annihilations distributed with a certain profile, which is called Navarro, Franken, and White. So what you are supposed to see here, and statistically you see it very well, is that without dark matter, you get an excess here that you can reabsorb, so these residuals go to zero, essentially, if you include dark matter. Basically, a sort of evidence of the presence of dark matter that is producing these photons from the galactic center. So this is convincing. Nobody's doubting this. There is something in the data which is not explained by, say, standard astrophysics of different sorts. Whether it's dark matter or not, that's it's another point. And it's debated since maybe 15 years or so. If we insist on the interpretation in terms of dark matter, you can make not only a morphology like I did before, but just a spectral analysis, and you see that you can fit the data reasonably well with a particle that has a mass of about 35 GeV or so, that annihilates into BB bar and has a thermal an annihilation cross-section which is very close to the thermal one that I mentioned before. So indeed, there is this famous paper with thousands of citations right now that says that this is a compelling case for annihilating dark matter in the center of the galaxy, because it's exactly what we were expecting. You can also change the annihilation channel, and you see that you move the mass a little bit around. So as I write here, this was or is still as good as it can get, in the sense that it's precisely what you would expect from a WIMP, annihilating into BB bar with some tens of, say, weak interaction mass and the thermal cross-section, distributed with the Navarro-Franke-White, which is the standard profile. So why this is not so easy and controversial? Because there are other constraints that come into place. For instance, and here I'm going back in history 10 years, but I will have then an update. So, for instance, this paper showed many years ago that the associated constraints from antiprotons that I mentioned earlier briefly show that there is a lot of uncertainty that can exclude or not the fit that I showed a little moment before, depending on many assumptions given by the propagation of these antiprotons in the galaxy, their distribution, and so on and so forth. So, antiprotons can exclude or not, this is not conclusive, people debate. Gamma ray constraints from other sources, namely dwarf galaxies and other possible targets, are also not conclusive because they cut through the region in a sort of excruciating way right here. So this is the best fit, and you have something that is not able to exclude nor to confirm. And also the CMB, so the fact that you inject energy in the initial plasma when you have annihilations of dark matter, so you can modify the CMB, but those constraints, by not modifying too much the CMB, also are not conclusive because you have that the best fit region is not completely ruled out nor completely confirmed. So as you may have noticed, these are old papers. These are papers from 10 years ago. Fast forward to last November, and things have not changed too much. So in these 10 years, people have considered more and more refined galactic templates for the astrophysics and for the statistical analysis and so on and so forth. The bottom line is that, for instance, in this paper by Silvia Manconi and collaborators 3 months ago, that still the constraints depend a lot on the assumptions that you take, and so you're not able to exclude or confirm this excess yet. So setting aside this exciting excess that people are debating again since 15 years or so, the current status of instead the constraints on this field is given by this plot here. So this is a famous standard plot where you have the dark matter mass here and the annihilation cross-section here. So you have the thermal cross-section indicated by cosmology, the thermal freeze out here. And these are the different constraints considering different messengers, so gamma rays, antiprotons, cosmologies, essentially the CMB or neutrinos. And you see a nice complementarity between different constraints that are dominated, say, here by the Fermi, by the dwarf galaxies, gamma rays from dwarf galaxies. Then antiprotons take over, and then also gamma rays at higher energies become the dominant one. Neutrinos are somewhere up here, and other constraints like the CMB or the BBN are sitting somewhere on this plane. So let me point out two obvious, again, frontiers. One is pushing down these constraints, looking for even more weakly coupled dark matter. And the other one is, of course, pushing this frontier, which is going towards heavy, say, PeV dark matter for theoretical motivations which exist, for instance, in non-standard cosmologies, and so on and so forth. Okay, so I think I did justice more or less to WIMPs, which are still one of the most popular candidates and explored in many different ways. Now, let's move a little bit and move, for instance, a little bit to the left to another set of ideas which we can call sub-GeV dark matter, which is less well defined, as you will see, but basically it means dark matter with a particle, with a mass that goes between 1 MeV and 1 GeV or something of this sort. So one can have the same sort of approach and say, is this motivated by theory and production in the early universe, and can I test it in the three complementary ways as I did for WIMPs? Well, you see that the answer is maybe. And let me start with the production and say, no, the theory motivations. So I don't want to enter too much into the details, but let's say that there are theory motivations for sub-GeV dark matter particles. And the first paper that mentions this idea, I think, historically, is this paper here by Céline Boehm and Pierre Fayet, that realized 20 years ago or more that actually if you assume that particles of dark matter are coupled to a new gauge force, so not the weak interactions but that were dominant at the time, but new gauge forces, then you could have a way to circumvent the Lee-Weinberg limit that tells you basically that particles have to be heavier than a few GeV, otherwise they're not produced in the right amount in the thermal freeze-out mechanism, right? So they say if we couple them to a new force, then their mass is free and can be lighter, and for instance, in particular, lighter than 1 GeV or so. This was sort of formalized in the obvious idea, if you think about it now, but at the time it was not maybe so obvious, of WIMP-less dark matter, so-called by Feng and Kumar, that and then you can describe it as a hidden sector dark matter or secluded dark matter. These are more variations of the same idea with a lot of complexity. That is basically the realization that the important thing that you need to have in order to have the thermal freeze-out working is that this annihilation cross-section has the number that I mentioned before. And this annihilation cross-section is given by a ratio of two numbers, right? So the weak coupling and the typical weak mass in the case of WIMPs. But of course, you can realize it with another ratio of couplings that boil down to the same value. Like if you have a new interaction with a certain alpha x and a new typical scale m, this m can be small, and so you can have a naturally small mass for the dark matter, a natural scale sub GeV, for instance, and still have the thermal freeze-out working out properly. So you will have interactions of annihilations of this sort that you have annihilations of dark matter particles into this new boson, say phi, that then mixes with the standard model bosons, and so this thermal freeze-out guarantees the right abundance of dark matter. So there are several other ideas that could motivate sub-GeV dark matter. I'm listing some of them here, but I'm not going to discuss them. I just mentioned the WIMP-less dark matter and this MeV scalar dark matter. There are many others, such as the SIMP miracle or asymmetric dark matter and so on. And my interpretation of all this is this a good theoretical foundation for WIMP dark matter? Well, sorry, for sub-GeV dark matter. Yes and no. Let's say my pragmatical attitude is to say, why not? So we have to not leave any stone unturned, and so people have explored also sub-GeV dark matter. It's less compelling, in my personal opinion, than WIMPs, because weak interactions are there, while these new interactions could be there or not. But still, we have to test it because why not? So how do we test it? Again, through direct detection, indirect detection, and possibly collider searches. So let me sketch briefly these two, and then move on to the next candidate. What about direct detection? Well, direct detection, as you can imagine, is tricky for these light particles because they are light, so they are sub-GeV, and so it means that when they hit one of the nucleus, they deposit little energy because they have a little recoil energy to deposit to the nucleus, and so typically this is below the threshold for a typical nuclear recoil experiment. Indeed, you see that in the standard plot here, all the bounds go up when you hit 1 GeV or a fraction of a GeV, right? So the idea is to use other targets, and in particular electrons, so scattering over electrons of these particles, or use nuclear effects such as the Migdal effect that allows you to be sensitive to small energy depositions, although this is not confirmed yet, or whole new experimental strategies like using different kinds of materials that can be sensitive to small energy depositions. So quite clearly, this is and the fourth frontier where experiments and theorists are pushing right now. What about indirect detection? Okay, so indirect detection, we said, means looking for charged particles, charged cosmic rays, or photons. And let's look first at charged cosmic rays. So you have annihilations of sub-GeV particles producing, as usual, say, positrons and possibly also antiprotons if they are slightly above 1 GeV. They go around, but the issue that you have is that they cannot enter the sphere of influence of the sun. Because it turns out that the sun has a magnetic field and a heliosphere, say, yes, that screens us from the entrance of low energy particles from outside, just because low energy particles cannot penetrate and are deflected away, okay? So you cannot have access to dark matter particles producing these low energy charged cosmic rays in the galaxy. With one exception, which is the Voyager spacecraft, because Voyager launched exactly when I was born, so 50 years ago, is still taking data and is still sending data to Earth, all right? So with the old computer sitting somewhere at NASA, they don't change it since 50 years. So they have, Voyager is taking data and would be able to see possibly positrons and electrons from outer space, because it's outside of it's one of the two spacecrafts which are outside of the heliosphere right now. And indeed, later we will see some bounds based on Voyager itself. What about gamma rays, or let's say soft gamma rays? Well, as I said earlier, dark matter annihilates and produces soft gamma rays, so typically sub-GeV gamma rays, because we're talking about sub-GeV dark matter. But here what you have is another technical problem, which is the so-called MEV gap. So the fact that if you take the sensitivity of all different experiments of the past decades as a function of the energy of the photons to which they are sensitive, you realize that they are very sensitive at high energy, say above a GeV or so, and they are several MEVs or so, and also at low energies in X-rays here, but you have a gap in the middle at the MEV range. And this is just due to technical stuff, the fact that, I mean, detecting an MEV gamma ray is not easy through Compton effect or through pair production, so you have a lack of sensitivity in the middle here. Luckily, there are new experiments which are coming up, including these ones here, that will fill a little bit this gap at some point. But for the moment, we are blind in this MEV gap here. So one idea that we had in the past is how to try to fill this gap here. The idea is quite simple and is to use inverse Compton scattering. So the idea, which I will not develop here, but just to give you a flavor, the idea is that if you have sub-GeV dark matter particles that are annihilating, producing electrons and positrons, and photons, instead of looking for the sub-GeV photons which would fall in this gap, you look at the inverse Compton scattering of the electrons and positrons on the CMB, for instance, or on the photons in the galaxy. And this will give you X-rays. So you'll give you a signal here where you are sensitive again. And so you sort of cheat and jump below this gap and become sensitive again. What is the status of these searches here? Well, again, so in this plane of now mass of dark matter in MEV, so we are well below a GeV indeed, and the annihilation cross-section, you have a busy plot, so a number of constraints, but have a look of the fact that we have bounds from Voyager, which are this one here, and bounds from inverse Compton X-rays, which are this line here, plus another number of things which come from different search strategies. So of course, this is another frontier, and people are trying to push with new experiments and new ideas towards the bottom right here. So just as an intermezzo, a little bit of say a different, the same idea applied to another system. It's contained in this paper here. So you realize immediately that you can do the same trick, so looking for inverse Compton scattering, also for WIMPs. So I talked about WIMPs earlier, so these are 100 GeV particles, right? Instead of looking for 100 GeV photons produced by these WIMPs in the annihilation, you look at the inverse Compton scattering of these particles and producing typically MEV photons, which will be detected by the new experiments that I mentioned a moment ago. Okay, so if these these are the constraints that I was mentioning earlier, the constraints from that busy plot. These are the sensitivities of the new experiments that will fly mostly this summer or in the following years. So we did this many years ago with Paolo, who's in the audience somewhere, and we applied again this idea to the new experiments in the MEV range here. Okay, so also here, searches are going on. And now let me move to something completely different that was mentioned yesterday. So let me jump to the high end of the spectrum and talk essentially about macroscopic objects and in particular primordial black holes, which are very popular since about 10 years or so as a candidate for dark matter. So why primordial black holes? We learned at school that dark matter cannot be an astrophysical object of some weird nature, such as, for instance, rogue black holes floating around in the galaxy or lost brown dwarfs or some sort of thing. Why? Well, because essentially of weak lensing, strong lensing, sorry. So the idea that if you have a population of these bodies floating around and making the dark matter in the galaxy, then some of them will pass through the line of sight of some distant source, and you would see it in the strong lensing campaigns. So this has been tried for many, many decades, and you have compelling constraints which are given here as a function of the mass of these massive astrophysical compact halo objects. You have the fraction of dark matter that they can constitute, and you see that basically you are excluded a fraction of a percent between 10 to the minus 11 solar masses and 10 to the 2, 10 to the 3 solar masses. Okay, so weak lensing kills you in this way. But even more importantly, we know that dark matter cannot be made of astrophysical objects because it cannot be made of baryons. It cannot be made of matter that we know. Basically because the BBN tells us that baryons are a limited number of the content of the universe, and the CMB even more precisely tells us that baryons are 4% at most of the content of the universe. So the loophole in all this is that you can have primordial black holes, right, which are produced before BBN, and so they, through primordial fluctuations, as Alessandra Bonanno mentioned yesterday, and so they are taken out from the count of baryonic matter in the universe, and they have a mass which is either too small or too large to create a problem for weak lensing, for strong lensing. So if they are too small, then simply the effect is not visible enough. If they are very heavy, then their abundance is small in the galaxy, and so the probability that one crosses our line of sight is reduced. And so you circumvent the lensing constraints that I mentioned a moment ago. They became very popular, of course, when gravitational waves were detected, because as Alessandra said yesterday, maybe LIGO and Virgo could have seen them, and some of the early events were interpreted as the coalescence of two of these primordial black holes. What is the current status? The current status is given here. So this is an extended plot of the previous one. This is the mass of machos or primordial black holes in grams or solar masses. These are the lensing constraints that I mentioned earlier. And you see that you have windows which could be open in principle around, below or above these lensing constraints. In particular, this window here, which is not constrained by anything still, and tells you that in between 10 to the minus 16 and 10 to the minus 11 solar masses, primordial black holes could be a good dark matter candidate. Now, what are all the other constraints? Well, the other constraints are due to the fact that, well, first you realize that the range of masses is huge, not the order 19 orders of magnitude, but still several, and it depends, their mass depends on the moment in which they are produced, roughly speaking, with this relation here. But there are many other constraints, which are depicted here in either blue or red, come essentially from one thing, which is the evaporation of the primordial black holes. So, as you know, by Hawking evaporation, these primordial black holes have a temperature that is inversely proportional to their mass, and they have a rate of evaporation, loss of mass, which is inversely proportional to the mass at the power 2. So, small black holes have evaporate quickly, and so very small black holes would have evaporated by now completely. Larger black holes would evaporate later, and in particular, primordial black holes with a mass of the order of 10 to the minus 16 to 15 solar masses, they would be evaporating right now, producing light particles such as electrons, positrons, soft photons, and so on, and so we can look for them. And indeed, people looked for them, for instance, using Voyager, using Integral, and using other soft photon detectors. So here is another obvious frontier, and you have to push it as much as possible towards closing this window, which is the still open one. Let me jump to the one-to-last candidate, which are sterile neutrinos, so essentially KV dark matter. So here I'm going very fast, and I will just say that this is, at least to me, only essentially phenomenologically motivated right now. So these papers from 10 years ago, there's nothing very recent here, so I just can go very fast. There are these papers from about 10 years ago that in some clusters, and also possibly in the Andromeda galaxy, detected an excess of a line at a few 3.5 keV. That you can obviously see along this plot here, which cannot be interpreted, at least from what people think, from any atomic transition, say. So what you have is that you can interpret this in terms of a dark matter particle, in particular a sterile neutrino that has a mass of twice the energy of the line, so 7.1 keV, that decays through this Feynman diagram, producing a photon, 3.5 keV line that we see, and the neutrino that will not detect. So you do the computation, and you find that the right flux that you need is given for a mixing angle of the order of 10 to the minus 6, 10 to the minus 5, or 10 to the minus 6 or so. So here you see the summary plot where you have the mass of this particle here, the mixing angle plotted on the vertical axis, and the excess which sits somewhere here, which is more and more in tension with several different things, including constraints from cosmology of different sorts. So here, obviously, there is a frontier of pushing towards this direction here. And the last thing that I'm going to mention is, of course, the very far left side of this plot, so axions and axion-like particles. So let me skip for this audience the theoretical motivation of axions, which is not particularly needed, I guess, but let me just show our plot, because there are many plots, but this is particularly nice because we did it. And so this is axion mass and axion coupling to photons, so the famous, say, Primakov effect coupling here. So this is the current state of the art, a bit simplified with many different experiments that we have summed up towards, compactified in some colored areas. And here again, the frontier is to go as low as possible in this direction here. Okay, there are many experiments, and I'm not particularly an expert on that. So in the last 2 minutes, just to conclude, what I've done, I've jumped about up and down in this parameter space and selected some possible ideas, some possible candidates. So the standard thermal dark matter, sub-GeV dark matter, primordial black holes, KV neutrinos, dark matter, ultralight dark matter, axions and axion-like particles, and so on. And what are my conclusions? Well, my conclusion is just that the physics of dark matter is in an experimentally driven phase. So there are experiments all over the place. And the thing is that theory is pointing to preferred directions, but actually too many, maybe, in some sense. Okay, so I pointed out these 5 categories here, and I have a summary sentence for each one of them. So thermal dark matter is still motivated, and the frontier is maybe to go to high energy, high mass. Sub-GeV dark matter is probably a why not possibility, but detecting it is more challenging because of the gaps and the different things that we saw, and so on and so forth. And if I have to summarize the searches, you see that the frontiers I have go in all the different directions, right? So that's my way of saying good luck to our friends experimentalists, and pick anyone you want, and you will certainly find something. Okay. There is also an energy frontier above there, but next talk. Okay, thank you very much.
Thank you for the nice overview and presentation. Questions?
There is a so-called memory burden effect for light primordial black holes. So what do you think of that?
The memory burden effect? Huh? So the memory burden effect is something that tells you that these constraints that I showed for primordial black holes are completely to be revisited. Okay, so the basic idea is that a black hole which is evaporating at some point stops evaporating and plateaus because the memory, so the information stored inside the black hole cannot be lost completely. Okay, so and the mass stops at some point, roughly a half of the mass of the original black hole that started evaporating. So if this is the case, then indeed this part here disappears completely, and there are current works that have recalculated this in this low energy, in this low mass regime. Yeah, I could have shown that, but yeah, I mean, it's not controversial in the sense that no, I think there are issues, but I mean, even Hawking evaporation, we haven't seen it. Yeah, so I mean, it's all in the same. If it's the case, then it can completely revolutionize this thing. Yes.
It sounds like nonsense. It sounds like nonsense.
Ask.
E to the s over 2 is much less than e to the s.
Mm-hmm.
Make a black hole with e to the s remnants. What's the entropy? Is it given by Beckman's Hawking? No. Right, then what is Beckman's Hawking?
Okay, no, there are some serious people that are investigating that, so, okay.
On the heavy mass side, using primordial black holes, you pointed out there is a window, but if it's not primordial black hole, you still have all the range of possibilities on the heavy.
No, here I would say that the things that people discuss are essentially primordial black holes, and actually you have to stop at some point here around the incredulity bound, which is the 10 to the 4 solar masses that I mentioned at the beginning. So actually the window is pretty much closed here. Okay, so now when I was pointing to heavy dark matter, I was thinking about particle dark matter, but much heavier than WIMPs, so at the PeV energies or so. And those are still particle candidates with a mass which can be heavier because you have say, non-standard cosmological histories that allow you to produce it in right abundance, even if they are heavier than what the unitarity bound would give you. The range can be wide open. So let's say the current interest is around the PeV, I would say, PeV, but it's mostly, I mean, probably because we are reaching there with experiments like LASO and GRAND and these other experiments, and so maybe it's a bit of a window of opportunity. I don't think there is anything that points to a specific value. Maybe Filippo knows better than me, I don't know.
Are there prospects in astrophysical searches, in astrophysics experiments, right? Not to search for dark matter, but to constrain its properties. You see what I mean?
Yeah. And the answer is no. I mean, let's say, no, from cosmology, you know only that dark matter has a range that sits in that thing, and you don't know essentially nothing about its interactions, other than slightly negative things, like it cannot be heavier, it cannot be stronger than something. From astrophysics, yeah, okay, so there are hundreds and hundreds of possibilities, like looking at the role of dark matter in compact objects, in supernovae, or other kinds of these, but then they are somewhere in the plots. I mean, I cannot point to anything specific. Like for axions, you can see that they can have a role in the explosion of supernovae, and so you can have a constraint, and it's difficult to say something generic, honestly.
In this context of the question, there have been efforts, for instance, in the bullet cluster to make statements about cross sections. So is there any way in which one can go beyond most naive model building and put constraints on pressure or dissipative properties on these small scales?
The bullet cluster gives you a bound, an upper bound on the self-interactions of dark matter particles with themselves, which is actually pretty loose. I mean, in the end, it's not particularly constraining. And there are other kinds of similar objects that give you bounds of the same sort. It's not particularly constraining. Yeah?
So yesterday, Alessandra was mentioning that the next generation of study of gravity waves can start having ideas of the medium.
Of?
The medium,
yeah.
where the black holes, is there, okay, I doubt, is there any way
No, there is. So actually, there is a strings of papers that ask the question, so the thing I can answer about is, if dark matter is made of primordial black holes, and maybe an admixture of primordial black holes and some other kind of particle dark matter, such as, say, WIMPs, can they live together or not? And basically, the idea is dark matter accretes around a primordial black holes, and the answer basically is no. So you cannot have both, because if it accretes around the primordial black holes, then you should see the shining in gamma rays, and the other way around, I forgot exactly, but yeah, so some of these constraints already exist. Then when we have also more powerful constraints from the merging of possibly these bodies, then we have, there are already some constraints from dynamical friction to the spiraling black holes that then coalesce. There are some constraints, yes.
In perfect time, we move to the next talk by Kostas Bakas on string theory and modern quantum field theory.
I have to hold this, right?
This is forward, backward, and the pointer.
Perfect, thank you very much. Okay, so let me start by thanking the organizers of this very nice workshop. I have been, I think, in GGI essentially since its inception in various functions or capacities, but I want to double down on the thing that Alberto said. I think one of my most exhilarating visits was the Lacey School, because, of course, you are in Florence, so, you know, this puts a lower bound on the attendance, and you far exceed it. But I was amazed by the spirit of the school. You know, students would hang around the whole time and keep forcing you to reply and so on. And this, we have a very successful school also in Paris, the Amsterdam, Brussels, Paris, Geneva school. And I think your school maybe was a little inspired by this, but somehow I found this one even more exhilarating. So please keep continuing, you know, the schools. I think they are a great service to the community. Now, after rather carelessly sending the title of my talk to Fulvio, and actually to Massimo, who has the same title, I realized I made a mistake. So I had to redefine my ambition. Obviously, you know, the title, you can see it here, spans everything. And I had to either be wise and choose one topic, which Massimo wisely did, or renormalize my ambition to doing better than ChatGPT. So I'll try to do this. Actually, Mark yesterday was telling me that you should put up the bound with perplexity, not ChatGPT. It's better, apparently, for what we do. But anyway, I ran it through ChatGPT, and I'm a little better, I hope. So where was string theory standing before GGI? This will be basically two transparencies. And you know, the common thing about GGI and string theory is that Gabriele facilitated the birth of both. So it started in '68, and then the big next step, conceptual step, was the realization by Ioneia and Serk and Schwarz that what was a nuisance, the spin-2 meson, which tended to be massless, was actually a great bonus because Einstein's theory of gravity was forced on you. There was no way you could avoid it. And then, you know, interestingly enough, if you look at Ioneia's paper, for the next 10 years it had 10 citations, which shows to you how little interest was in this idea. And then, until Green and Schwarz managed to show in a beautiful calculation that this was indeed a finite theory of quantum gravity. In particular, it avoided anomalies, potential anomalies, in a new way, to which I will come back. Then the next few years, you know, there was crowds working on this. It was quickly realized that there was potential to unify all forces. That was clear. And by exploring the landscape of four-dimensional string theories, and by also controlling much better what is nowadays called stringy corrections or alpha prime corrections, one very quickly bumped into this practical problem called the landscape. So huge number of possibilities, at least at this level, of perturbative string theory. How do you find our universe? Is there a principle that chooses it? Sure, we had traded the parameters of the standard model for dynamical fields, but still the problem was, what do you do with this? Now, so, you know, the mantra back then was go beyond perturbation theory and all your problems will be solved. And indeed, in the next few years, in particular during this golden period between 95 and 97, there was a large number of developments that gave us the first serious, very solid look at how the theory looks beyond perturbation theory. It started, I'm very schematic, I mean, lots of people did marvelous work on this. Started with string dualities, which allowed you to say that the ultraviolet theory is most likely unique. Then a really great step was taken by Polchinski, who realized an amazing fact that there are string solitons. You know, solitons you have to solve nonlinear equations. It's a horrendous task in principle. And somehow you could do it in string theory by words, by saying, well, these are things on which open strings end. And furthermore, they had this unique new feature. Solitons have zero modes. For instance, Goldstone theorem tells you there's a translation mode. So if they are extended like a domain wall, these become massless scalar fields. But in this particular case, these zero modes, because of supersymmetry, completed spin-1 multiplets, but more interestingly, because of this deep brain structure of open strings, they completed non-abelian Young-Mills multiplets. So, you know, non-abelian theory is living on these solitons. And then this, you know, led to many great developments, in particular, the first microscopic model of Bekenstein-Hawking's entropy calculation, and finally, maybe the last really revolutionary idea, which is ADS-CFT, and on which I will now come back. In a word, basically ADS-CFT tells you that string theory in a box, a gravitational box, confining things in the interior, is really a quantum field theory. Okay, so this brings us roughly to the GGI years. And I think what happened next, that's my personal take, I mean, people have different opinions, is 2.5 things, I would say. One is that we have learned how to prove in a physicist's way, and more particularly to decipher and to exploit ADS-CFT. And there is really a lot of progress there, many more open questions. I think Massimo will tell you much more about this in the next talk. But at the same time, and I think that's equally interesting, there is something I would call quantum field theory generation Z, you know, partly inspired, partly in symbiosis with string theory and condensed matter physics, which has the marvelous advantage of basically your fantasies become an experiment if you are in low dimensions at least. So partly from both sides, quantum field theory, I think, has been transformed, and I'll try to tell you a few things about that. Now, how about the original dream? I mean, you know, particle physics unifying cosmology and maybe some experimental test. Clearly, that's the place where there has been very little timid progress, but still some progress, and I think that's where one needs new ideas, and some luck, including experimental luck, which unfortunately LHC didn't provide us. So my talk will be broken down along these three lines. Let me start with ADS-CFT. So very quickly, you all have seen these ideas, I suppose. As I said, solitons have 0 modes. They are massless excitations along the world volume of the soliton, but they are localized in the transverse dimensions. And in deep brains, these come in Young-Mills supermultiplets. They are non-abelian because an open string, oh, I'm moving forward, has 2 endpoints which correspond to color charges. And the rest is because of supersymmetry, namely the Goldstone bosons of transverse translations completed by fermions and gauge fields to make supermultiplets. Now, the key idea of Maldacena was that if the tension is very large, so if you have a lot of these things, the number of colors is very big, this must back-react. What corresponds then to a back-reacted domain wall is some kind of black brain. Oh, I'm sorry, this is the older version of my transparencies. I try to modify it, but anyway, what I should say here is an extremal brain, not a black brain. And therefore, there is a horizon. The horizon, all horizons have this property of infinite redshift, and 0 modes of the original story could now be replaced by closed strings infinitely redshifted at the horizon. So there's some kind of low energy limit from both sides. Here you only take the 0 modes of the solitons. Long wavelength gravitons decouple and you throw them away. And likewise here you take everything redshifted at the horizon. Long wavelength gravity modes don't see this very narrow tube, so they also decouple. Now, so unlike the other dualities, ADS-CFT relates a quantum field theory with quantum gravity in a box, and therefore this gave for the first time a non-perturbative definition of what quantum gravity could be, albeit in a very restricted context, namely anti-de Sitter space-time. And now there's the prototypical case, which is n equal 4 super Young-Mills dual to one of the string theories, type 2b in ADS5 cross S5. And here are some entries in this dictionary. N equal 4 super Young-Mills is a conformal theory, so you can talk about local operators, in particular single trace operators, F mu nu, phi, and so on are matrices, adjoint matrices. So single trace operators are single string states. The dimension and the spin of the operator becomes the energy and the spin of the state. In particular, one privileged operator, the energy momentum tensor, is the graviton. And crucially, the 2 parameters of this theory, the number of colors and the 't Hooft coupling, become basically the radius of ADS4 in the 2 fundamental units, which are the string scale. So this controls 't Hooft coupling stringy corrections, and 1 over n controls quantum gravity corrections. Now, this is an example of what one calls top-down holography. So this means that the quantum string theory is known in the ultraviolet. You know exactly what's going on in the UV. You also know exactly what the dual conformal theory is. This is very nice. The problem is that typically these are unrealistic field theories. They are brain engineered, and they are very rarely coming close to what we really want to know about strongly coupled field theories. However, in this context, a very convincing test of the conjecture has been derived in the years 2000, and this corresponds to the exact derivation of the spectrum of operators in the planar limit, but for all values of the 't Hooft coupling. Now, this is a real mathematical tour de force. It basically started with the idea that you can think of these symbols, F, mu, nu, phi, d, and so on, as spin states, the letters of an alphabet, and therefore this is some kind of spin chain of the type that condensed matter people know how to deal with. And lo and behold, it's an integrable spin chain. And as you go up in powers of the 't Hooft coupling, the Hamiltonian becomes less and less near neighbor. However, you can still integrate. And now I won't tell you more about this thing. It took about 10 years to arrive at what is nowadays called the quantum spectral curve. And that's a very impressive achievement. For instance, if you look here at two operators of dimension and twist 2 and 3, one of them is the Conici operator. And you can do both weak coupling expansions. Well, this is not the Conici, it's some related problem, but you see you can go up to a huge number of loops, planar loops always, and you can also do a strong coupling expansion, and very nicely the quantum spectral curve, extrapolates between the two without phase transition, which tells you that you are indeed talking about the same theory on the gravity side and on the quantum field theory side. So that was very impressive. In particular, let me stress that this goes beyond kinematics and symmetries, which was the original fear. Okay, is this all fixed basically by conformal symmetry and supersymmetry? Well, some of these operators are not protected. Actually, all the non-protected operators grow to very large dimensions at strong coupling, and it's clear that this quantum spectral curve, comforted the idea that the duality is really there. Now, it has two drawbacks. First of all, it's the planar limit, and remember 1 over n is really quantum gravity, whereas lambda 't Hooft only controls string key corrections. That's one problem. The other is that it gives the scaling dimensions. It doesn't give the OPE coefficients, the 3-point couplings, and there is considerable ongoing effort to actually, at least in the planar limit, compute also the OPE coefficients. There are some new techniques, I will say a word later about, supersymmetric localization and the bootstrap, and people are trying very hard to go further in this direction. There's another direction also that has been exploited a lot, namely you count operators of a given dimension. If this dimension is large enough to correspond to a black hole, maybe basically scales like the number of colors square, you can compare to the Bekenstein entropy, and you can do this for supersymmetric black holes, again, with marvelous localization techniques. You can compute finite volume or mass corrections, and it all fits very nicely. So I think this is great mathematical physics. It has used and developed actually very powerful new tools. The results confirm ADS-CFT, but one maybe can say that there were no surprises, no new lessons in this. It's great that you can do it, but what's next? What do we learn really about the two? So at the other extreme, there is something called bottom-up holography. Now here, you take the opposite point of view. You say, suppose there is a CFT with some type of spectrum. Then I write down some kind of low-energy effective gravity, which has the corresponding fields for each operator, and some phenomenological Lagrangian. And then, of course, you are much more flexible, but the question here is this real, or does it lie, as one says in Swampland? Now, Swampland for string theorists means that there is no ultraviolet completion, no real theory in the UV. For condensed matter people, it rather means that there is no ab initio theory, so no cutoff theory that flows to this in the infrared. So the typical story is that you say, okay, I have a conformal field theory. It always has an energy momentum tensor, maybe a conserved current, some scalar operators whose dimension can be either relevant operators or marginal. Now I write down a gravity theory that has the graviton, U1 gauge field, moduli, marginal deformations, and relevant massive negative mass, actually, fields in gravity, which is okay in ADS. Now, this has been a very rich activity. It has led to all sorts of new strong coupling models for possible strong coupling phenomena. ADS CMT for condensed matter theory, has been an active field for models of things like strange metals and quantum phase transitions. And ADS QCD also has given nice intuitive pictures for things that we expect, like confinement and chiral symmetry breaking. Some people in the audience have worked on this. The problem here is that it's not quantitatively precise. On the other hand, big plus is that it allows you to study real-time phenomena out of reach of numerical simulations, in particular transport at finite temperature and chemical potential, and very far out of equilibrium physics. And it has also greatly enhanced our understanding of horizons. So my next two small topics will be about this. But Massimo will talk much more about that. This transparency I can possibly skip because Urs gave a beautiful talk yesterday about using this for the quark-gluon plasma. An early spectacular indication by Polycastro-Son and Starinets was to simply say, okay, if finite temperature means there is a horizon, the generic black horizon is the one of Einstein theory. So let's calculate this quantity, which is shear viscosity, how effectively you transfer momentum across layers of flow compared to entropy density. And they found this rather universal answer. And now, this is quite spectacular. I'm not here, I'm a bit out of my depth, but Urs can step in. But as far as I understand, every other possible fluid you can think of, in particular perturbative QCD, but also liquid helium or cold atoms at the unitarity threshold, are much, much more viscous than a black hole horizon. So this seems to be a rather extraordinary fluid, and Urs gave a nice talk about what you can do with this. However, the more recent thing, which I find very interesting, is what about trying to do something about non-supersymmetric horizons and the real quantum gravity, not planar limit, but really try to think about 1/n, and also get rid of supersymmetry. So this, allows you to try to make a step towards the real black holes. Unfortunately, not extremal spinning black holes like the ones of Alexandra's talk, but you can do something about a system that is similar in a ways, which is the charged black hole, the Reissner-Nordstrom black hole, at extremality when the mass is equal to the charge in Planck units. Now, this solution has a horizon which is, again, anti-de Sitter 2 times the 2-sphere, which is the horizon. And the Bekenstein-Hawking entropy of this system is basically area over 4g newtons, so it's pi times the radius squared. And this is expected to be the number of ground states. E to the S0 is supposed to be the number of ground states. And note that this controls quantum gravity corrections, because when the black hole is small, well, then it starts being more quantum, and this is controlled, of course, by the radius RH. Now, there was a surprise found in this system, because naively you would expect that, well, ADS2 means you have conformal symmetry and you have this large degeneracy of ground states. But it was found that there is one low energy gravity mode which splits this degeneracy. It has strong dynamics near the horizon. And at the end of the day, rather than having ground states with this huge multiplicity, you rather have a density of states that goes like this. It goes to 0 at 0 energy, but it has a huge exponent in front, so it quickly rises. And actually, since n is finite, the spacing of energy levels is basically controlled by 1/n. And it was found also that this typically has the form of a random matrix model. Now, this kind of low energy dynamics is captured, as I said, by the Schwarzian mode of a Kaluza-Klein reduced Lagrangian. You start from 4 dimensions, you forget Kaluza-Kleins on the 2-sphere, and you go down to basically a theory where there is a single dynamical guy, this phi mode, the Schwarzian mode. And Kitaev made the rather amazing observation that he knew about a system that has very similar properties. Now, this is very unusual because who would have guessed that this disordered system, you know, Mark is not here, it's basically a system where you have what did I do? Sorry. Can I get rid of this? Thank you. So it's a system which has basically Majorana spinors at fermions at different sides. It has 4 side couplings which are disordered. There is no spin-glass transition, but it's still a disordered system. And it was written down in early days by Sage-Defanier, who were trying to find solvable models of spin liquids with no quasi-particles, but Kitaev noticed that this theory, which can be solved exactly by using the Schwinger-Dyson equations, has actually an emergent conformal symmetry and has precisely the spectrum lifted at very, very low energies that I showed before. Emergent because you see if you write down the Lagrangian, there is also a kinetic term, a psi dt psi. So the two together, the full theory coming from ultraviolet is not conformal, but if J is very large and this term dominates, then you have some conformal regime, and then at very low energies, you break spontaneously the symmetry and you get the spectrum there. So, this is a very nice solvable model of what maybe a chaotic black hole horizon could look like. And let me only make one comment which makes people wonder about the real meaning of this duality. As I said, JT gravity does reproduce this density of states, which is self-averaging, actually. So you get the same result for any sample in the n goes to infinity limit. However, you can also try to calculate something else. For instance, the correlation function of 2 partition functions. So you have 2 replicas. They are at different complex temperatures. This thing, never mind the details, it's called the spectral form factor, and it has a lot of information about the energy spectrum beyond this density of states. And actually, the result of the calculation in JT gravity matches the qualitative expectations and the numerics of SYK, even though, well, yeah, for large A, this is not self-averaging. It matches it, but at one expense. You have to sum in your gravitational path integral wormholes. Now, these are basically, think about 2 black holes related by a tube. So, now there are 2 horizons. The 2 replicas can live in 2 different horizons, and somehow summing over these geometries is crucial for getting back the SYK model. Now, this is very confusing because somehow, how does this reconcile with top-down or exact holography? In top-down holography, you would think that there should be no connected correlation between Yang-Mills theory and its copy, so maybe wormholes should be ruled out in fully fledged quantum gravity. But then if one doesn't have this fully fledged quantum gravity, only a low energy gravitational path integral, what does one exactly compute? And it seems here that what you are computing is obviously some kind of disorder average, some kind of quenched disorder. This seems very weird for quantum gravity, so it has to correspond to some kind of uncertainty of the dynamical theory, which is still not understood. That's all I wanted to say about this. Let me come now quickly to the second topic, which is quantum field theory in the new age. So as I said, it has developed hand in hand with string theory, and I will be very quick about some landmarks. So first of all, three things I won't talk about, but which are very important. Supersymmetric quantum field theories, in particular this new technique of localization, which tells you that when you integrate in field space, most of the orbits cancel out, give zero, except at fixed points of this supersymmetric measure. And this, has extended a lot the original works of Zyberg and Witten in all sorts of directions, in particular computing these black hole entropies for supersymmetric black holes. Amplitudes, you know more than I do. You gave the Galileo Prize to some of the people that made great work on this. Bootstrap, well, again, it's amazing how things resurface. Perturbative string theory, Gabriele's amplitude, in a sense, grew out of the analytic S-matrix and the bootstrap idea. And the Belavin-Polyakov-Zamolodchikov world sheet paper also was basically the first very nice use of conformal bootstrap, which is to say that I only use basic things like causality, unitarity, some high energy fall-off, and crossing symmetry, and try to solve these constraints. Now, the modern revival was prompted by this unexpected efficiency of the numerical CFT bootstrap of Ricardo and company, signaling that somehow, truncating, level truncation or truncating operators converges really extremely fast. And this has now grown into a very active area of research. There are 6 or 5 or 6 no-mass white papers that have bootstrap in the title, and I won't say more about it. I suppose Ricardo will. So this is beautiful technical progress. It has been integrated in areas where high precision is needed. We heard about gravity waves and QCD yesterday, critical phenomena also. But let me here mention 2 other, maybe slightly more conceptual developments in quantum field theory. One is defect symmetries and anomalies. There is a workshop coming up here, I think, in a month or 2. And this is an interesting story because, of course, in string theory, we are all used to the existence of extended solitons of any dimension. But this has ushered in a revival of one nowadays called defect CFT or QFT. And one can essentially summarize it as follows. QFT is not simply local operators and Green's functions. There are these non-local observables, which are equally important, and sometimes they play the role of order parameters. We all know about the Wilson-Polyakov loop being the order parameter for deconfinement, and magnetic impurities having essentially initiated the modern renormalization group. There are also infrared safe observables like this so-called ANEC or light ray operator, which gives you very nice calorimetric observables for QCD in particular, but more generally for what is called conformal colliders. And with help from both holography, the bootstrap, and supersymmetric DCFT, this again became a very active area. I will only focus in one corner, which is quantum symmetries and anomalies. So how am I doing with time? 5 minutes, oh, okay. I will be very fast. So, our current understanding of symmetries was developed in the 60s and 70s. Symmetries can be global or gauged. Gauge symmetries are redundancies, always intact, whereas global symmetries can be explicitly, softly or hardly broken, spontaneously broken, or have anomalies. And QCD exemplifies all of them. There is gauged color symmetry, an exact baryon number symmetry, an approximate flavor symmetry. spontaneously broken axial symmetry and an anomalous U1. And anomalies are obstructions to gauging, which are preserved by RG flow. And in particular, it was one of the nice early realizations that because gauge anomalies have to cancel in the standard model, quark-lepton families must be complete. Now, the novelty in the 80s and 90s basically comes from three places. First of all, since one had these extended objects and corresponding gauge fields, one could talk about P-form symmetries. These are symmetries that don't act on local operators or states, but they act on these non-local objects. In string theory, these are P-branes. Secondly, for different degrees P and Q, these don't have to commute. And actually, the Green-Schwarz cancellation is, in a sense, an illustration of this thing. Here is a quick way to understand it. If you take, say, a U1 gauge theory with chiral fermions and the Stuckelberg mass, where A is an axion field, but you also couple A to F times F dual, then the gauge transformations of A have to transform also the axion by shifting the axion by lambda. And to cancel the gauge anomaly from the chiral fermions, you use the fact that these two classical terms together break gauge symmetry, because if you shift A by lambda, as required by the first term, you generate, of course, an FF dual term, which is the anomaly. So this, in a sense, the new thing is that it's not a classical symmetry that's anomalous. It's a symmetry that's only there in the quantum theory. It doesn't exist in the classical theory. You need the quantum theory to cancel the classical anomaly. And this is very closely related to another phenomenon called anomaly inflow, quantum anomalies on soliton world volumes cancelled by classical topological bulk terms. So I think I'm running out of time. However, well, there is one application I could have talked to you about, but these ideas have led, to a new view now of symmetries, which are generated by topological defects, which can be non-invertible, and group theory is replaced by something called category theory. For instance, P-form symmetries of different order don't need to commute. There is a nice application for Yang-Mills theory at theta equals to pi, which basically shows that you cannot have a normal unbroken confining phase at theta equals to pi for this Yang-Mills theory. And it's actually the main theme of a lot of condensed matter physics and quantum tensor networks, which have the symmetry-protected topological phases, these bulk things that cancel anomalies. The last thing I will only show you one of those is that purely from black hole thought experiments, people came up with general properties that work in quantum field theories without gravity. One is this one that I won't explain, comes from the SYK sort of model. A very nice one is that there is a very solid, rigorous argument to Bekenstein's very heuristic arguments, which said that, quantum information, entropy S, cannot exceed the energy times the size of a quantum state. And now this has become a rigorous bound by using a very smart trick, positivity of relative entropy, and the fact that if you take the half line, then the state looks thermal to an accelerated observer, essentially. And so you can write it as a thermal state with a Hamiltonian, modular Hamiltonian, which is the thermal boost. So this is the inequality, the von Neumann entropy is bounded above by this thing, which is energy times length or radius. I don't have time to go this. I will just say a few words to conclude about the third problem, quantum gravity and unification. As I said, the original hope was to have sharp predictions on BSM and maybe beyond Einstein gravity. Since this stumbles upon this vacuum selection problem, people said, okay, but at least let's try to limit effective field theories. How do we do this? Well, we don't know how to do it either because we are not smart enough or because it's fixed by anthropic considerations, an unfortunate possibility, but we can at least try to constrain them by using the consistency with an ultraviolet completion. This goes to under the name of landscape versus swampland problem. There are no general proofs, but in a sense, these arguments point to loopholes where you should look at if the conjectures were not obeyed. I want to just show you, so this can become sharp if you make extra assumptions. There is a nice application to infinite distance limit telling you how far fields can travel in field space. That's relevant for inflation models. There's one that I find particularly impressive. It's a paper called Where is String Theory? And what these people did is the following. They assumed that the effective field theory is simply maximal supergravity in more than 4 dimensions. And then they said, let's try to constrain the coefficient of the R⁴ correction. So you could try to do this with dispersion relations, but they went further. They did some kind of non-perturbative numerical bootstrap, and the result is here, and it's very impressive. So they found that this is the allowed range of this parameter alpha that multiplies R⁴. This is easily excluded. In between, they don't really know, but with their numerical accuracy, it's also excluded. Now, the interesting thing is that this whole allowed space is exactly covered by string theory. This points to some kind of string universality in the UV. String theory is unavoidable. Whatever you can do consistently comes from string theory, but of course that's only a very small step in this direction. Now, to conclude, all this is very nice, but I think there is obviously, everyone in this game knows there is one elephant in the room, and even if you try to hide it, it comes back and hits you. There is no controlled vacuum with broken supersymmetry, and this is a difficulty identified early on. Unlike gauge symmetry, supersymmetry restoration seems to require infinite volume limits, and there is no stable 0 lambda vacuum at weak coupling from non-perturbative effects. And in the 2000s, a new type of compactification showed the possible route out, but it remained, to my mind, inconclusive. And it's still very unclear whether these are just technical problems or much deeper. One may actually hope they are much deeper, and there's something very crucial we miss about the IR-UV connection to try to make progress on this field. So with this, what next? As you know, theorists are very bad on this because if they knew, they would be writing a paper, not giving a talk. But I like this line. Actually, I heard it from Mark, who was paraphrasing or quoting Giorgio Parisi on spin glasses. He said, if you find an interesting physics problem, follow it to the end of the world. I would add that, okay, that's obviously quantum gravity is interesting, but the fact that all these new math tools keep crossing one's horizon is also a big encouragement. And with this, I will first like to wish happy birthday and many thanks to this wonderful institute and everyone making it work. And I will leave you to ponder a poem about Giorgio's, a more poetic expression of Giorgio's phrase, which is this poem. I won't read it, I'll let you read it while you ask questions.
Thank you very much. Thank you very much for the very nice overview and with prospects and problems. Any question?
We are busy reading
this maybe is covered by the next talk. So, but in case, Anything on the supposed resolution of the information paradox, black hole interiors, right. Maldacena work? Okay, then okay.
I don't see other questions, so we can have now the coffee break. We can, let's thank the speaker again. And we can have, contrary to the schedule, we can have the coffee break until 11:30, half an hour, so more relaxed. Please. Please. Shh. Let's start the last session. We'll have the second talk on quantum field theory and string theory by Massimo Porrati.
Questo va avanti, questo dietro.
So let's start with this second review talk, and I will start it using a different technique from Costas. As you know, so I call this l'histoire d'un surface, because essentially I will do like in novels. You know, when you have to describe a very long and complex historical period, you can use many characters seen by an omniscient eye that sees everything and moves all these characters, right? So that would be, for instance, the Dream of the Red Chamber with its 700 characters, War and Peace, Les Miserables, the Tale of Genji, even, where Genji dies in the middle. Or you can follow one family, one character, and through that see the historical period. Buddenbrooks, the Sea of Fertility, for instance. Here I'll adopt the second technique, and I'll track the development of what we had in string and field theory through the evolution and refinement of a surface, a minimal surface, which geometrizes entanglement entropy, and appeared actually more or less at the time when GGI started in 2006. Now, of course, when I say that area is proportional to entropy, I'm talking about a much older story, a story that began with Bekenstein and Hawking in 73 and 74, who established that a black hole has an entropy proportional to the area, is area divided 4 times the Newton constant in natural units, h bar equals 1. Now, after that, we had many works, a lot of work, and in particular work starting with Strominger and Waffa that in '96 convincingly showed that in some special cases we can actually see that the entropy of a black hole is statistical mechanics. It's the logarithm of the number of microstates. Right? Now, in a few weeks, there will be a workshop here. So let me go back. It's this one, right? Okay. This is it. Yep. In a few weeks, there will be a workshop that I think will uncover much more about this. So stay tuned. Now, the original result in used supergravity. I should mention supergravity is the 50th anniversary of the discovery of supergravity also. Supergravity was used in a fundamental way to derive the result of Strominger and Waffa, essentially for 2 reasons. In supergravity, in the supergravity theories that describe string theory, type 2a, type 2b, there exist extremal black hole solutions that preserve some of the space-time supersymmetries. Some are lost, not all. And when you have some supersymmetry, there exist quantities. There is an index, which is essentially the number of bosonic degrees of freedom minus the number of fermionic degrees of freedom in your system, that is coupling independent, and then you can compute it into regimes. You can compute it in a regime where some coupling constant, the G generically is small, and then you can do a perturbative counting using some of the techniques that were reviewed by Costas earlier, right, the brains. But then you can increase the value of G, arrive at the opposite limit. At the opposite limit, you have the description in terms of, say, D brains is strongly coupled, but you have a geometric description where you discover that your system of D brains actually describes a black hole. But the index is invariant, so you compute it here, it's the same there. Right? So that was an important tool. Now, as Costas mentioned, again, in another important progress in understanding the relation between area and entropy was the ADS-CFT duality, late 97, which says that quantum gravity in anti-de Sitter space, in d+1 dimensions, is the same theory as a conformal field theory in D dimension that we can think of as living on the boundary of anti-de Sitter. Anti-de Sitter topologically is a solid cylinder here, described here. So you have a quantum gravity that lives in the bulk, but this theory is the same as a conformal field theory without gravity living on the boundary. When the theory in the bulk is strongly coupled, the CFT is weakly coupled, and vice versa. That's why it's a duality. Now, again, our gold-plated example requires supersymmetry. The conformal field theory living on the boundary is 4-dimensional supersymmetric Young-Mills theory with 16 supercharges. The theory in the bulk is type 2b supergravity on a DS5 cross S5. Because of all these supercharges, we can perform many exact checks of the duality. We cannot prove it, but we can perform checks because of supersymmetric non-renormalization theorems and other properties of supergravity. So again, some cheers for supergravity now that it has hit 50. Okay, now when you what I described before, that cylinder was a vacuum, say maybe with a few excitations, but in ADS-CFT, of course, you can describe whatever quantum gravity state you have in the bulk. So in particular, you can ask, what is a black hole in the bulk? So this fuzzy line is supposed to be a black hole. Well, through ADS-CFT, we identify the black hole in the bulk with a typical thermal state in the CFT with a temperature that obeys the standard thermodynamical properties. Right? Given the standard formula. So what is a black hole in the dual? Well, it's a typical state at a given temperature, when the temperature is high enough. I won't tell you what is this high enough. Okay, but now let's go to something else. We were talking about surfaces and information. Well, as you know, quantum information has left the realm of theoretical speculations. It's a tool. It's relevant to physics. It's relevant to cryptography, computer science, finance, and banking. I think that at Riccardo's institution, there are people studying quantum cryptography and not just to decode black holes, right, but just to communicate between banks. So one of the very, very basic quantities of quantum information is entanglement entropy. It's essentially the building block of almost everything else. So what is this? Well, I mean, if you have a system and this divided into two subsystems, right? Its Hilbert space is the product of the two, HA cross HB. This is technically a lie, but not a big lie. In quantum field theory. So if you have a Hilbert space for the system A, a Hilbert space for the system B, you can take the density matrix of the combined system and say trace over A. That will give you a reduced density matrix rho B, or vice versa, and say you can define the entanglement entropy of A as negative trace on the Hilbert space A of the density matrix rho A log rho A. This entanglement entropy can be non-zero even when the total state is pure. Right? So that's why it's called entanglement. Now, there are generalizations that have been used in the study of black holes and quantum information theory and quantum gravity. And So in particular, one entropy that is very useful is this Régnier entropy that has this form. It's useful because computing the trace of rho to the alpha, especially when alpha is integer, is easier than computing the trace of the rho log rho. And these entropies have a limit in which they reduce to the entanglement entropy. So this, in the literature, many times this object is computed for alpha integer, then an analytic continuation is done to all alpha, and then you take the limit alpha going to 1. Okay. Now, we gave a few examples before in which holography geometrizes quantities, right, in a field theory. So you see, we have a thermal state is geometrized by a black hole in the bulk. And you may say, well, what then in holography, what is it that geometrizes entanglement entropy? Well, you may say, suppose that we have a boundary theory with two boundaries, A and B, right? If the boundary A is small, you may think that it's reasonable to suppose that only a small part of the bulk can be reconstructed just by the data in A, right? If instead the A is very big, you may think, well, we can reconstruct more of the bulk, right? And then, of course, the question is, what is the dividing surface? What is the dividing surface that tells me which part of the bulk can be reconstructed from some boundary data? Right? The answer came about at the same time that GGI started in 2006, and the answer is this surface. It's the minimal area surface that's homologous to A and with the same boundary. So you take this boundary A, well, it ends here at these 2 points, and then you take a surface that is anchored at the same 2 points and can be deformed into A, and try to find what's the minimum, right? Then the area is the entanglement entropy. So you have a refined and sometimes not so easy to compute quantity in field theory that can be computed geometrically in the bulk. Okay, so, well, the original recipe was, in 2006, was not covariant. The covariant generalization was given shortly thereafter, in 2007. And then corrections to this formula were proposed in 13 and 14 by these authors. And actually now the idea is that this minimum surface is not exactly what Ryu and Takayanagi proposed, but it's a surface that gets a correction. So this is called quantum extremal surface, just to distinguish it from the classical one of Ryu and Takayanagi. And this surface in the bulk can be computed semi-classically in an expansion in Newton's constant. It is the term that we expect, the area of the surface H here, divided by 4G, right? Plus the entropy of the bulk region A. Again, you have to anchor this, the surface H at the boundary of A, and the surface has to be homologous. So you have to take a Cauchy surface, find the minimum, then move the Cauchy surface, find the largest minimum, and that's the quantum extremal surface. So with this formula, actually, we get something interesting. So let me start with a trivial case and a silly example. Right? So let me start with the case where actually I don't anchor that surface at all. Right? So I said, okay, why don't I take a closed surface in the bulk, and the bulk is actually has a very little entropy. So the entropy of the bulk could be a pure state or a state with a few excitations. Its entropy is much less than the area of a surface H divided by 4G. So take, for example, A to be a pure state, or the vacuum. Well, then what happens? How can you make this generalized entropy as small as possible? Well, since essentially S bulk is 0 or close to 0, it's very easy. You make the surface dividing A and B smaller, right, until it disappears, right? So the minimum area surface is just nothing. But this means that actually, not surprisingly, maybe we discovered something that sounds a bit trivial. With the data of all the boundary, we can reconstruct all the bulk. Right? That doesn't seem so surprising. But the story becomes more interesting in a less trivial case. So here, what I have. Here I have a conformal field theory, but I change a little bit the story. I have a conformal field theory that is coupled outside the boundary of ADS. So this disk is a Cauchy surface of ADS. Time is perpendicular to this slide. Right? What I do is the following. Let's take a conformal field theory, couple it to a bath, a thermal bath, and allow an interaction between the conformal field theory and this thermal bath. The thermal bath is a field theory. There is no gravity in the bath. There is gravity inside the ADS on the disk, but not outside. Right? So we give leaky boundary conditions to the ADS. And maybe we have a very entropic state here, for instance, a black hole. So in this case, what happens? Right? What is the minimal surface? Well, this story actually is related to the page curve problem of a black hole that was mentioned earlier, but let me review this. The entropy of radiation as computed by Hawking is due to the entanglement of the quanta that fall behind the horizon of a black hole with the quanta that escape the black hole, eventually arrived at the conformal field theory, and in the case of these leaking boundary conditions, actually continue and enter the bath. Right? And so we can take, so the entropy of radiation is the entropy of what I call the surface B, what was outside the black hole. Notice that I tricked you a bit because I also had a B inside, which will play a role, but let's start with the standard case. So radiation escaped your box, right? The Hawking quanta are entangled, and so the radiation keeps growing with, I mean, this straight line is a moral straight line. In reality, I mean, I have to fudge the units here, but it grows, right, with time, indefinitely, it always grows. Okay. On the other hand, one of the properties that also Costas mentioned is that entanglement entropy obeys an inequality. The difference of the entanglement entropy for region A and for region B in absolute value is less or equal than the entropy of the total region of SA united B. So in particular, if the original state of black hole plus whatever is outside the black hole was pure, right? A is equal to B. The entropy of A is equal to the entropy of B. You can also prove it from the definition that I gave earlier. So, well, what happens here? Then you said, okay, then the evaporating black hole has an entropy. The entropy is proportional to what I called earlier S sub A, right? But S sub A at some point goes to zero because the black hole evaporates, the area goes to zero, the black hole disappears. So in reality, the entropy of radiation should grow, but then arrive at some point and start to decrease, right? Because SB is equal to SA. So, I mean, you cannot have the entropy of radiation to be very large and the entropy of the black hole being zero. Right? So the real curve of the radiation should actually be whatever is bound by the two curves, the increasing curve SB, entanglement of radiation, and the decreasing curve SA, which is the entropy of the black hole that evaporates, hence it decreases. And the turning point is called the page time, right, which is roughly of the time in which half of the mass of the black hole has evaporated, give or take. Okay, so we have this problem, which seems to be in direct contradiction with what we said before, but actually the quantum extremal surface now comes to the rescue. So now we will put it to some good use. So suppose that now we are in a situation as I described before, leaking boundary conditions here, radiation that leaks into a thermal bath, these arrows, and then, but the entropy in the bulk is actually pretty big. So suppose that now you do something different from what I did before. You take as region B the bath region where the radiation ends, but also some unspecified region in the middle. You call both B, and whatever is left you call A. Well, in that case, you want to see what is the minimum extremal quantum surface. If the region inside had very little entropy, we saw before what would happen. The minimal surface would be shrink to zero. But here, you have a black hole inside. A black hole has a very high entropy, right? So, actually, the situation changes a bit, because now you can find a minimum generalized entropy, an extremal quantum surface, by putting a surface at the boundary of the highly entropic region, the inside of the black hole, right? And this is a region where the area is finite, because it's 4 pi times radius square in 4 dimensions, right? So in this case, actually, the quantum extremal surface does not shrink to 0. Okay, and remember, the quantum extremal surface tells you, it bounds the regions that you can describe holographically from the ones that you can't. So, actually, this idea was proposed by Pennington and collaborators, Almeri and collaborators in 2019, and it's called also the island proposal sometimes. So, the point is that this generalized entropy that determines the quantum extremal surface is, let's take a case in which it's essentially the entropy of the black hole. Then what happens? Well, what happens to our page curve and to the minimal surface? When the black hole starts evaporating and time is much less than the page time, right? Then actually the entanglement between the radiation and the entanglement of the Hawking radiation is small. The generalized entropy is SA, right? I mean, you just, there is no advantage in creating a surface that carries a lot of entropy. Your generalized entropy is just the entropy of the region A, on the entire region A. Here I took a simple case in which A plus B is a pure state in order to avoid unnecessary complications. Now, instead, when you are well past the page time, there are many, many quanta, right? That, so in the Hawking radiation. The Hawking radiation is highly entangled. The region B decreases the entanglement. I will be more specific in the next slide. So actually, the way to get a minimum extremal surface is to say that the region B is this plus that. I made an assumption that I have to justify that these two regions together have a low entropy, right? You gain something by putting a surface here, but not much. So the generalized entropy then becomes essentially the entropy of this area, A divided 4G. And now the entropy of radiation, since the state is pure, is actually this entropy, the entropy of the surface, but the surface shrinks to 0, right? So before the entanglement entropy grew, and now instead it decreases. Now, to be more specific and make more clearer what I mean, let me notice that actually the formula that I gave here was derived in various contexts. I derived it in a DSCFT, but it's not limited to a DSCFT. This formula applies also to asymptotically flat spacetimes that we may be more interested in. So this formula actually has a more general validity. And to understand better how the page curve problem is resolved, we can simply say, why don't we do it also for black holes in ADS or in flat space? After all, even when we studied the ADS case, we had to fudge with the rules of ADS-CFT. We had to allow for leaky boundary conditions and allow for a thermal bath in which the radiation from the inside could escape, right? So what is the story in flat space? If you believe in holography, you may say, well, you have some region A, right? And then let's say that the black region is the black hole, the region inside the horizon. Well, let's put a screen just slightly outside of the black hole, and that's the region in red, right? And let's put a holographic screen, like you do in ADS-CFT. So let's suppose that actually you have a theory on the boundary that encodes whatever is inside. So the question is, does it do that? So what happens in this setting? This setting is essentially the one that I gave you before, but generalized to the case where we don't care about what happens far from the black hole. We zoom in the horizon. At a time much less than at the page, all the region A, the inside of the black hole, is encoded in the holographic screen, which is the boundary of this fuzzy red region. I called it S. I didn't write it on the slide. the minimal surface, the extremal quantum surface is actually 0, it's nothing. All the entropy that of the Hawking quanta is due to entanglement, right? So the generalized entropy on the screen, actually, well, this H is nothing, it's the empty set, is simply the entropy in the bulk, that for a state that was pure, A plus B was pure, then this is the same as the bulk entropy of A. So you have just a few quanta, you start with a pure state, you entangle, there will be some entanglement entropy in A, some small entanglement entropy, that's what this generalized entropy is. It's not surprising. Then, what happens when you are well past the page time? Then, if you keep entangling the inside with the outside, the bulk entropy it becomes very, very large. So, actually, you can decrease the total generalized entropy. You can find a minimum at a fixed Cauchy surface, at fixed time, if you want, by actually putting this surface H essentially at the horizon of the black hole, and calling the region B, what I call B, so namely the region that cannot be reconstructed from the hologram, calling the region B also the inside. So now we have changed the rule. Now there is a region outside the screen, but also we call B the region inside the black hole. Right? So this is B. Now, what do we lose when we try to minimize the entropy? Well, we lose something because we have to add a surface at the boundary of the black hole. So the entropy will increase by area of the black hole divided 4G. Right? On the other hand, now the region B is the sum of these two. And in this region, inside plus outside, actually, the state is pure. Because Hawking radiation entangles the state a quanta inside the black hole with quanta outside, but the total state is pure, entangled but pure. So we gain this A over G, but we lose S bulk A, which means that we have something with less generalized entropy. So what we have is that A, we have a holographic string. B, there is an extremal surface that sits more or less at the black hole horizon. And C, the holographic screen does not encode the information inside the black hole. The information inside the black hole is encoded by the Hawking radiation. And so, and this is just because you decrease the entropy due to the fact that the sum of these two regions, I mean, the theory on these two regions is in a pure state. Okay. So now you can see the page curve, and it will emerge exactly as it is. At T page, the generalized entropy stops being dominated by the entanglement entropy of Hawking quanta across the horizon and becomes dominated by the Bekenstein-Hawking term. So it increases and then decreases, as it was supposed to be. Okay. The price that you pay is that your holographic screen does not reconstruct inside. That information had to be reconstructed using the Hawking radiation that escaped past the screen. Okay, so now I want to give you, maybe this is one of the business transparencies here. I want to give you at least an idea of how this generalized entropy arises. Well, there are many ways of deriving generalized entropies. There are ways that have nothing to do with holography, but since holography is a team, right, we can do this. So I wanted to show you that there is a system in which if you assume the old formula of Ryu and Takayanagi, then you derive the complete generalized entropy with also the bulk entanglement entropy of region A. So the classical Ryu-Takayanagi formula actually gives you immediately the generalized formula. If you construct a system that may seem a little bit baroque, but is quite interesting in its own. So what you have is that you start with an anti-de Sitter theory in one more dimension, so say in D plus one dimension. So you have a bulk that is D plus one dimensional. Then you cut off the boundary of this D plus one dimensional ADS, but in this way. First of all, you use coordinates for ADS that have this form. Here I gave ADS 3, and time runs perpendicular to the slide. Right? So this is a fixed time section. So you do the following. You have a bulk anti-de Sitter. Then you cut off the anti-de Sitter d plus one dimensional space by, well, here you are exactly at the horizon. So this region, you are exactly at the boundary of anti-de Sitter. Here instead you cut, but not at finite distance from the boundary, but at a finite angle in these angular coordinates. So these are angular coordinates in the plane, in the theta rho. So why you do that? Because now here you have a CFT that lives exactly at the boundary. There is no gravity. But in this region, you have cut and you go away from the boundary. So in this region, you have an anti-de Sitter space in dimension d with gravity. So now you have a system where you have gravity on this anti-de Sitter space, no gravity. You see, quanta can freely go from one to the other, leaky boundary conditions, right? And then a global bulk description. So you have two holographic descriptions, the bulk, this anti-de Sitter, and the boundary of the boundary anti-de Sitter, which is this clown's nose here. And okay, this is just the line of, this is the radial coordinate and theta is the angular coordinate. This is the Karch-Randall model. It was proposed in 2000 for other reasons. But it's very useful because it allows you to study systems where the entropy, where you can study the leaking of radiation in very geometric terms and the effect of matter in very geometric terms. So in this case, let's say what you do. Well, in this case, in Karch-Randall, the quantum extremal surface is just the geometric HRT surface, Hubeni, Ragamani, Ryu, Takai, Yanagi. Because now, in the bulk, everything is geometric. There is no space for matter, for entanglement, for anything like that. So you have a conformal field theory that is dual to this anti-de Sitter, but is coupled to a bath, and then there is a big bulk description that is even bulkier than this one. S bulk A, right, is already encoded in geometric quantities. So, so what happens here? Well, you have leaking boundary conditions. So to stop the leak, you put a brane that reflects quanta. So you make this region impermeable to quanta by putting what is called a Cardi brane. So at this point, you decouple the region to the left to the region to the right. At t equal to 0, the state on the dynamical anti-de Sitter boundary here is pure, the entropy is 0, and the minimal surface, the Ryota-Kanayagi surface, is just this point. Then you change, then as t increases, you drop the brane and you let quanta go freely from the left to the right. In this case, you have a leaky system where radiation can escape from this part of the boundary. But in the bulk, everything is geometric. So what is the generalized entropy in the bulk? Well, it's just a geometric brane that goes from here, to the beginning of the brane. But remember, the Cardi brane keeps dropping down. Right? So at some point, it drops down so much that the surface that goes from here to here has a bigger area than a surface that goes from the boundary to the horizon of the black hole. And so here you see the passage from the two cases, right? Quite geometrically without introducing any matter contribution. All the matter contribution to the entropy is geometrized by this bulk. Now, the area of this object is not particularly obvious if you look at this, but is actually proportional to the area of a black hole that I put on the anti-de Sitter space. So I get exactly what I want. Right? Okay, so this was just a case to show that we can geometrize a lot of things. Let me give you some other example. There are other surfaces that want to tell a story. An interlude is what happens in flat space. In flat space, in asymptotically Minkowski space, all null geodesics end on what is called the null boundary, Scri plus, and come from Scri minus. As Scri plus, the metric has this form, expanded in powers of the radial coordinate r, right? And the boundary of Minkowski space has a component, a null component, where null geodesics end, that is r times S2, where S2 is a celestial sphere. Now, what is nice is that the S matrix in momentum basis can be transformed formally into a correlator of primary fields of a strange, non-unitary conformal field theory by a change of basis. So you write the S matrix in this theory, and then you notice that there is a transformation that I gave here, where the S-matrix elements can be transformed by an integral kernel, which is the bulk-to-boundary propagator for a massive scalar. Here I have massive scalars propagating, right? And when you do this operation, you end up with objects that formally look like correlators of primary field in some unknown conformal field theory. What is more interesting is that certain limits in the S-matrix, for instance, the collinear limits, become the OP limits of the conformal field theory. And so actually you can see that this mapping becomes quite precise. You have a mapping from an S-matrix to a conformal theory, and which reproduces the basic properties of conformal theory. So what happens when two operators become close together in the coordinates theta. 1 year ago, many developments of this initial idea were worked out in a workshop here called From Asymptotic Symmetries to Flat Holography. So this is a field that also was discussed very much here. Okay, now let's go to the last case, de Sitter space. In de Sitter space, you can extend the quantum extremal surface formula. Now you may say, where is the boundary? Well, the boundary exists if you take a static observer and you look at anti-de Sitter in static coordinates, because in static coordinates there is a horizon, and then the rule is that the surface, I mean the extremal surface is a surface located at the horizon of the static de Sitter space. And here is the formula for the metric of de Sitter in static coordinates. So at r equal to h, you have horizon. So you see, if you, this observer does not see all anti-de Sitter. It sees only this region. Well, it sees only this region and can send only signals to this one. Okay. The quantum extremal surface formula can be extended to de Sitter. By the way, there is an interesting property of de Sitter space that if you take any matter configuration, you compute the bulk entropy and the area of the horizon perturbed by the presence of matter divided by 4G. This is less than the entropy of pure de Sitter space, which the entropy of pure de Sitter space is also the entropy of a certain state called the Hartle-Hawking, which entangles the two static coordinates patches. I mean, you have to make a maximal Cauchy surface, you need a patch from me to the horizon and the patch from the horizon to an antipodal observer. Right? And the state that entangles the two, the vacuum state computed using a functional integral rule is called Hartle-Hawking, and this state has this entropy, which is bigger than all the others. So the interesting thing is that in this theory, you can compute the relative entropy of the static patch for any configuration. So you can compute the maximal entropy minus the generalized entropy of any matter configuration. This thing can be computed rigorously in perturbation theory in G Newton. And you may say that this looks strange because actually the algebra of local operators, observables in quantum field theory, in any quantum field theory, in particular quantum field theory here, is what is called the type 3 von Neumann factor, an algebra that admits no trace. So how can you have no trace and you have an entropy? Well, the trick is that actually key to the computation is that to compute an entropy, you need an observer. So you need to introduce a quote-unquote observer with a Hamiltonian Q, a canonical coordinate, and then the total Hamiltonian of your system is the Hamiltonian of the rest of the world plus the Hamiltonian of the observer. Physical states commute with this total Hamiltonian. You can write states that do commute with this Hamiltonian in this way. And what happens is that Q and these rest operators generate an algebra that is called type 2, a type 2 factor. Even when the local observables are type 3, this algebra is type 2 and it admits a trace. Okay, so so OFIS commutes with the generators of all general coordinate transformations. And so, for instance, this operator I called OFIS is not really a local operator because it has to commute with all the generators of the diffeomorphism that act trivially at the observer in this case. So if you say, if you have a time translation, you decompose time translation into one which has vanishing integral over your entire surface plus the rest, and essentially this O has to commute with the modern language with the BRST language, BRST operator associated to the other transformation. So, well, I mean, I spare you some paid advertisement for my work in view of the time, but you can, with Antonio, we found a very nice method to start with an algebra of local operators and construct this O hat, which does not require to know much about the algebra itself and the gauge theory. So let me skip this. In any case, it's just, again, paid advertisement. It's better if it's subliminal, you know. So let me come to summary and conclusions. We have used the quantum extremal surface to illustrate one of the many pathways along which theoretical physics developed since the founding of GGI. If I want to describe it in a word, this path is geometrization of quantum information. Holography suggests that there are subtle quantum information quantities in a field theory that become very obvious, not so subtle geometrical objects in a dual theory. I gave an example. Other examples that have been studied in the past are complexity, which is conjectured to be dual to a certain volume or classical action of the bulk geometry, and the list is growing. Now, the surface still has a story to tell us, son histoire. In particular, we still don't have a clear universal consensus on whether the black hole horizon is singular, if there is a firewall, or it's regular. We have arguments that go both ways, and what I told you in this talk does not really distinguish between the two. So with this, I thank you. I thank GGI for these 20 wonderful years, and I hope that by Keplerian estimates, it lasts at the very least another 20 years, if not much more longer. Okay. Thank you.
Thank you, Massimo, for the nice talk. Any question? Clear to everyone. So, no question. Let's thank again Massimo. Before going for the last talk, I just wanted to say that if someone is not on rush for traveling, there is a lunch served here as yesterday at the end. Okay. Please, Riccardo.
Thank you. So this is to go, how do I go ahead? No. Oops. Okay. So how do I get the image? Sorry, questa qui. Okay. So in line with the previous two talks, I chosen this title. Okay. In reality, I'm gonna talk about this. Okay. I'm gonna try to connect things to stuff that we could do in experiments, okay, hopefully. So this is a sort of perspective talk, or I cannot say it's a review talk, and it's also based on recent work that I've done with these people, in particular with these two former students of mine, Alfredo Liotti and Lorenzo Ricci, so young students, some more seasoned researcher. Luca Vecchi is one of my main collaborators. And also work that is about to appear with much more seasoned colleagues. Okay. So going back to what Gabriele was saying, the GGI is coming of age, becoming an adult, and at that point you start having some existential questions, okay, about the activities that are happening here. Okay, so QFT is bread and butter of our activity, and I think it's worth asking ourselves, why is it worth studying it, okay? And there are many motivations that anyone can think of, and you can hear. The safest one is that, well, this is a necessary step to build one day the theory of everything from which everything will become clear, okay? And to do that, you don't even need to know the things that will become clear, so you don't even need to study the standard model, okay? You just aim at the theory of quantum gravity. Okay? So if you want to be more specific, and these are answers that are given by young people. Okay? So you say, oh, I want to understand strong dynamics, confinement in QCD. And then, of course, there's always the nice possibility to connect with the condensed matter zoo, where there are lots of experiments. These are pretty safe statements, okay? The first one, I mean, this is like building cathedrals, okay? It's a very noble endeavor. Put bricks, okay? Hopefully it's Notre Dame, not the Tower of Babel, but you can justify it, okay? And then there are more concrete reasoning, like truly supporting the experimental program. No perturbative QCD, no collider physics, okay? So this is very clear. And then you come to more questionable activities, okay? Trying to really explain directly the open questions of particle physics, hierarchy, flavor, unification, and which amounts to building models, okay? And we know that this is an activity that leads to a lot of frustration, maybe that we don't have yet the tools, okay? And we are using more rudimentary ideas that truly are needed there. Still, I think it's necessary to do it, to see at least how far we can go and how much our ideas, how much experiments tell us about what we can do, okay? And of course, in this case, the risk of being, rather than builders of cathedrals, of being builders of barn, shacks, okay? But still, I think this should be done. My favorite one is the last, okay? Get inspired, okay? And if there's an idea, follow it. Maybe not to the end of the world, but at least until you can follow it, okay? Now, let me get back to physics, okay? I'd be curious to hear your comments about this question, okay? You can send them to me privately. Physics. So one start fact of physics is the existence of, sorry, I should do like this, is the existence of broadly separated scales of length, okay? This is a fact. This is a boon for physics because physics exploits this separation of scales to develop systematic descriptions, effective theories that can give precise predictions, okay? In fact, physics is the science of scale separations. Atomic physics, celestial mechanics, they're all based on that, okay? But it's also an embarrassment because we essentially don't understand the origin of this separation of scales. Certainly the biggest one, the one associated with the vacuum energy, the cosmological constant, we don't understand it, okay? And it's possible that our not understanding that implies that whatever we try to do, there we basically don't have any idea rather than anthropics, okay? It could be that that also sheds indicates that it's futile to think of the other problem, the one associated to the electroweak hierarchy, but actually, truly, we don't know, okay? You can also find arguments for why the cosmological constant could be anthropic and the hierarchy problem may not, okay? And I think it's worth considering the second possibility, okay, and see where we go and what we can learn from experiments, okay? So let me get back to the hierarchy problem or the hierarchy paradox. The hierarchy paradox or the hierarchy problem, no matter how you want to name it, is something that you can argue about simply by looking at the standard model Lagrangian, thinking the standard model as an effective theory, as we should think it of, right? When it was introduced, it was just a bunch of operators that you can put on a shirt, okay? But we understand, again, that all of physics is effective theories. And when you do that, okay, and when you write the standard model as an effective theory, you have to introduce a length scale or a mass scale that controls the expansion of, or call it multiple expansion. And when you do that, something really comes to your face and appears, is that there's a distinction, okay, in structure between what you can have, what you have in operators of dimension less or equal than 4, and what you have in the whole tower of higher dimensional operators, okay? In the sense that in the d less than equal 4, very limited number of things can happen. You have a lot of really special symmetries, accidental relations, okay? While in the rest, everything can happen. And it turns out that this separation also goes along with observation, okay? Observation speaks in favor for the simplicity that you see in this part, which is the part that remains when you send the fundamental scale to infinity. Okay? And this, we know it very well. It's the accidental origin of baryon, lepton, G. Now, this possibility, which is suggested by observation, however, conflicts with our theoretical bias, according to which we expect that one particular operator that exists here also goes up when you send the scale m star to infinity, okay? And that's the Higgs mass. And, okay, I cannot go back again to tell you this. This is the typical expectation from quantum effects, okay, that you expect. And if you require that there is no clumsy, implausible cancellations, you deduce this constraint. And this constraint really conflicts if you are really general about what this structure could be, okay? So you could say that the hierarchy problem or paradox is a clash between simplicity, the simplicity of observation, and the naturalness of our theory expectations. And now, when the hierarchy problem was formulated in the 70s, we hadn't done yet much model building. It's in doing model building that it took more this form, because the construction of all natural models shows precisely what you're fighting on. In all these models do not have, by construction, the nice property of a standard model. In these models, at dimension less than 4, or at the dimension where things become visible, you tend to see all this structure. And so you have to go through some clever set of assumptions, the model construction, to get this to work, okay? And so let me tell you slightly something more about this relation, something that I had to force myself to, in explaining, convincing colleagues that have the usual statement, this is not a problem, this is not well defined, I use dimensional regularization, all crap like that, okay? And actually, this formula is on the same footing as the formula you learn and love to use when you start doing general physics, okay? Which is the result of dimensional analysis. Dimensional analysis is just matching, if you want mathematically, matching the charges under dilatations of all the expressions that appear in the left and the right. Here, the dilatation of the units of time and length, okay? Now, these are symmetries. They are symmetries that are broken by your parameters, but yet you can use them. Symmetries are useful also when they are broken. And here is the same thing. Here you have dilatation, which is dimensional analysis. And here you have the higher spin symmetry of free field theory. Free field theory is a theory with a lot of conserved charges. Okay? The number of particles in each momentum cell is conserved. And these conserved charges precisely tell you that here you should have a square power of the top coupling, and also of all the other couplings in the theory. And in fact, in all the models that you can construct with the Higgs mass is calculable, you get that. So this is truly the result of the basic of physics, okay? And the hierarchy paradox is truly fighting with the basics, okay? We are going back to the point where we don't seem to understand what we learned on the first days of our studying physics. Now, let me get a little bit more technical or formal, and try to discuss more this issue of separation of scales and how they can originate. And this brings in the notion, this is one way in which the notion of conformal field theory enters particle physics. Let me explain this. So imagine a situation where you have a separation of scales, okay? So you have two scales in physics. So far it could be the bottom mass, could be the top mass, two widely separated scales, okay? Already the statement that there are two widely separated scales means that when you do experiments in between these two ranges, nothing really new happens. You don't discover anything. It's always the same. So in other words, the physics in this range is scale invariant, approximately. And scale invariance, okay, can be a symmetry of quantum field theory. Actually, when it's coupled to Poincaré invariance, invariably gives a bigger symmetry known as conformal symmetry. So this is how conformal symmetry enters. This is one door by which conformal symmetry enters the particle physics discourse. Now, now, given that, the question, okay, of how plausible, or if you want to have natural, the existence of separation of scales can be phrased in the language of conformal field theory, or if you want, in the language of RG flows. That is the same language that we use in statistical mechanics, okay? So there are two broad ways in which we can consider a separation of scales to be effortless, if you want, natural. The first one, I would call it marginality, okay, is the situation where you don't have essentially mass terms, okay, where all the scalar operators that you can add to your Lagrangian to generate a mass scale in the infrared have dimension close to 4. Now, an example of that is Yang-Mills theory. Of QCD is slightly more complicated. Think of Yang-Mills theory. There, the leading operator has classically dimension 4, and quantum mechanically acquires a slightly positive dimension. And given that the anomalous dimension is small, it takes a long time for this perturbation to become large, and this generates a big hierarchy. Of course, you always need a seed to generate this hierarchy. Okay? In the case of Yang-Mills, you should have a coupling that for some reason at the cutoff starts as weak. Okay? Okay, but you don't need an exponentially big hierarchy to start with. Okay? And the other is symmetry-protected marginality. You could have truly operators dimension less than 4, but they could be protected by symmetry. And we can discuss whether we like that or not. Now, having said that, now you can, it's worth using this notion and consider the simplest example of effort in trying to turn the standard model into a new theory that satisfies both simplicity and naturalness. Okay? And this example is offered by the idea of, very nicely and simply, these are our examples of conformal technicolor as formulated by Lutin Okui in 04. So, okay, let's take the standard model. That's our theory below a TV. Okay, that's where we essentially, let's say where we have tested it. And we would like to replace this theory with all these nice features, in particular, the fact that flavor is only controlled by a limited number of couplings with the same structure as the Yukawa coupling. We would like to replace this theory with the theory with that features, but with a theory that does not have this bothersome dimension 2 mass term. Okay? So what you do, you assume that the Higgs is actually part of, say, a conformal field theory, and the Higgs field is replaced by some operator, and the mass term is replaced by some other operator that you can, is what plays the role of H dagger H, but it's going to be a composite operator, I mean, that you cannot even write down, some abstract. And of course, you will always have this unwanted stuff, okay, that contributes to epsilon k, all the things that, the modification of the standard model that we don't see. And now, how do the wishes of putting together simplicity and naturalness go? They go like this. So first of all, simplicity, you want the scale, the UV scale to be very, very large so that you see as little structure at low energy as experiments indicate. But you want to nonetheless have visible fermion masses. So you want this operator that controls fermion masses to have dimension close to 4. Okay? So that amounts to asking the dimension of this operator is 1 plus a small quantity. On the other hand, you want naturalness, so you want this operator to have dimension close to 4. Okay? So this is the notion of marginality. So stated this way, this is a well-defined request in conformal field theory. Okay? By the way, these issues were debated here in 2006 during the first workshop, okay? I remember around that time. And let me show you how. So you can phrase this question as a request. Your dream theory, the theory that puts together simplicity and naturalness, it's a theory that in this space lives roughly here. Well, if you're slightly more, it depends on the hypothesis of the flavor theory, okay? The dark red, if you want to be robust, the other area, if you are willing to make more hypotheses, okay, to have a more structured flavor sector. Okay, and the question is, do you have theories here? Okay, notice it's a bit weird. Okay, in this region here, you would have an operator of dimension 1, for which, or close to 1, for which the dimension of the square is 4. Okay, it's like you put together two objects of energy 1 and 1, okay, and the energy is 4. Of course, you can say there's a repulsive force, and this can happen. But conformal field theories are very special and very constrained. The question whether this can happen, okay? And this is how the revival of the numerical bootstrap came up. And it worked very well, okay? It worked better, if you want. It was surprisingly well. And the first result is that it ruled out this possibility, okay? Physics doesn't give you, so this dream situation doesn't exist in nature. It's not possible, okay? And it could have ended there, okay? It could have ended there. And in fact, it ended there as concerned, at the moment, as concerned particle physics. It may not have completely ended. Maybe I will comment in a moment. It went on elsewhere, okay? It went in other directions, okay? It went, see, la fisica è come il maiale, okay? Good things, you can use everything, okay? You can use, and actually, rather than helping us with the hierarchy problem, it ended up giving us a tool, and Alessandro is here, and collaborators are the leaders in this field, in the study of conformal field theories, in particular conformal field theories in 2 and 3 dimensions that are relevant for statistical mechanics. And this is just an example of what the latest computations of the critical indices in the lambda point of liquid helium, okay, that obtained using the bootstrap, compared to Monte Carlo and compared to the data. As you see, they agree theoretically, but there is a many sigma deviation with experiment. This is experiments that I don't know how much it counts in this. This is a transparency that I stole from Slava Rychkov. Okay, this experiment here, okay, or a significant part of this constraint is coming from an experiment done on the space shuttle, because you have to do it in conditions where you don't have gravity, so you can reach the critical point everywhere. Otherwise, on Earth, pressure depends on the position, okay, and is not a homogeneous. So there is a big disagreement. It would be interesting to repeat the experiments. So Alessandro was telling me there was a proposal to redo it on the space station, but it didn't pass. Anyway, this is just to tell you that we follow ideas, and the ideas may go to other parts of the world, maybe not to the end of the world, but to other parts of the world, or maybe in space, okay? Now, back to particle physics. Mi manca 20 minuti. Okay, back to particle physics. So, again, in team with Galilei, there are 2 chief systems that you can broadly, okay, there is a galaxy in the between, there is a distribution, but there are 2 chief systems that you can imagine, okay, that the data are telling us, okay, as regards the hierarchy. Whether you want to give importance to simplicity or naturalness, okay? If simplicity is what really matters, then the best thing is that the standard model is just the right theory up to some very high scale. At that point, our stability, the smallness of neutrino masses, the validity of the CKM paradigm, they just follow without any effort. Of course, we don't understand why the electron is lighter than the top, okay? But that's exactly in the standard model. The inability to predict gives you the paucity of parameters that can fit the data nicely. And then the mass of the Higgs is beyond naturalness. Could be the multiverse. In the recent years, we had ideas, okay? These are all multiverse and relaxation, naturals. They're all related somehow to cosmology, okay? In that sense, they are a little bit murkier than the other approaches to the hierarchy problem. Maybe we're still in the beginning. I mean, it would have been worth a little review. I don't have time, so I don't do it. Anyway, my favorite possibility on this ground is this one, okay? Maybe there is something really deep, because, see, physics is based on effective field theories, always. You always separate scales. But eventually, if it exists a theory of everything, the theory of everything is it's a theory of everything. It's there. There's no effective description that we can come up with. So in that theory, maybe there are symmetries that, or like T-duality, that mix IR and UV, and we cannot see them in effective field theory, and maybe the hierarchy problem is pointing in that direction. The other possibility is the more standard one, the one where we can talk to our experimental friends, and where naturalizing new physics is at low scales. And in that case, you have to sweat with clever model building to match the constraints, to satisfy the constraints set by flavor, in particular in CP. Notice, however, that in this situation, there's an opportunity, okay? Now you really have to upheave all of flavor physics, and maybe now you may even have an opportunity to explain things, okay? And now, I think that and of course, there can be intermediate situations. I think that in that respect, so I want to give you now a brief cursus of where we stand on that, okay? I think this is a necessary exercise, if you want an activity, to even understand what we are learning from particle physics data experiments, okay? I think I don't need to tell you, but I have the impression that it should be reminded, okay? Okay, I'll discuss two examples. They all have to do with compositeness, okay? The first is modern composite Higgs, okay? As I told you, if you want to make the Higgs composite, again, what you have to do, what happened here? These are not visible. Oh, damn it. Okay, here is the standard model, and here it's a CFT. It's the CFT that contains the Higgs. So you assume that above the weak scale, the theory decomposes in the standard model without the Higgs, and another sector that eventually will give rise to the Higgs. And these two sectors are coupled through gauge interactions, and the fermions of the standard model, elementary fermions, are coupled to composite operators, okay? And they're coupled linearly. The reason why you need to do it this way is imposed on us by the properties of conformal theories. There's no way to separate scales if we do it bilinearly, okay? And below this scale, the theory is there's an effective field theory description of this physics that you can parameterize with a few parameters. If you want, this is a sort of educated SMEF. I insist on educated because SMEF is very uneducated, okay? But let me go on. So now, immediately, when you work this, when you take this, which is basically forced on you, you cannot do much else, okay? As I told you, the bilinear coupling of fermions to the Higgs sector is not available if the Higgs is composite, so you have to couple linearly. And this is you can think of this to be some conformal theory. We'll have fermion composite operators that have the standard model quantum numbers. Okay, this is a big request. Okay, if it has one, it will have a tower. We call them Regge towers, and there will be several of them. So there are going to be operators with varying dimensions, okay? Imagine you have many, so there are those that they couple to the Qs, to the Ds, to the... it's a bit far-fetched. And let me parameterize the dimensions of these operators in this way, corresponding to the fact that when gamma is 0, the corresponding mixing is at dimension 0, so it doesn't run. Now, assume that these dimensions now come one bigger and bigger than the other. These are the properties. You really see that, right? Because dimensions of operators, when you put the theory in the cylinder, are energies. So any theory that has positive energy will have levels that go up and up. So these dimensions will start from a minimum and go up, okay? And now what happens? Something very interesting happens, because now you look at the RG evolution, if you start from a very high scale, even if you start in a situation where these mixings are all anarchic of order 1, unavoidably a structure is generated, okay, where one vector is bigger than the other, but bigger by powers, ratios of scales, okay? So in other words, you generate easily, in fact too easily, a hierarchy among fermion masses, starting from a situation where you don't have anything, any big difference. The difference in mass between the electron and the top is simply due to the fact that there's a big separation of scales over which their couplings drift, okay? And as time goes by, people change. People may not like each other, okay? Over a long time, things happen, okay? And over a big chunk of running, parameters can become very different. Now, I'm speaking about CFT. CFT, do I know what I'm talking about? I'm not entirely sure, okay? The question is, you can ask, do you have a real theory realizing that? And the answer is no, Okay, of course not. We have at least holographic realizations. Okay, the Randall-Sundrum model is an example of that, where you can actually map geography in a slice of anti-de Sitter to parameters and phenomena. Okay, for instance, the mass of the KK modes is the mass of resonances. The KK coupling is associated to the effective coupling among these resonances, or if you want, to the number of degrees of freedom of the theory. In the notion that we know from large N QCD, that when the number of coupling of degrees of freedom grows, the coupling among resonances decreases. Okay, 1 over root n if you have a single trace, 1 over n if you have double trace, and that. Now, this is another example, beyond those that were commented this morning by Costas, of use of ADS CFT. He mentioned ADS CMT and ADS QCD. There, you're using ADS CFT to try to model known systems, okay? Here, I'm using it to explore the unknown. Now, let me tell you, do I think this construction necessarily corresponds to real physical CFTs? Most likely, certainly not for all of them, because these theories have continuum of parameters in the 5D description, and we know that CFTs form a discrete set. Okay? They form a discrete set in theory space. So most likely, most of these. However, there are recent studies, in particular by Stergiou and Osborne, and Stergiou and Richkov, that try to count the number of CFTs that you can form, at least in Wilson-Fisher fixed point, as you add the number of fields. It grows very fast. So it could be that the zoo of CFTs is more populated than we think, and maybe this is an animal that could exist there, of course. We don't know. Now, more to the phenomenology, I'm saying the Higgs is composite, so you would expect this like any other resonance, but actually this is not what we see, so you should separate it, and we know how to do it in QCD. If the Higgs is a Goldstone boson like the pion, this is what happens. And very much like for the pion, in any specific model, up to a few parameters that you always have, but generically what you get is something like that the mass of the Higgs will be controlled by the standard model coupling themselves and the overall scale. This is like the raw mass, and this is like, it's very much like what happens in QCD with the pion, where you have the role of this coupling is played there by alpha electromagnetic and the quark masses. And it's interesting to see, it's important really to assess where we are with the test of this idea experimentally, to ask where should you sit if you want to have a very plausible theory where you don't play around with parameters. Well, the resonances should be below, say, half a TeV, and the VEV of the Higgs should be of the same order as the VEV at the scale of the sigma model, the decay constant of the pseudo-Goldstone boson system. So in other words, the ratio V square over F square, you can see, is really the parameters control how much tuned the system is. Okay? And the question is, you can view experimental searches. One way of looking at the experiments is to see how big is the tuning based on what we've seen so far or not seen so far. You can say, oh, this is a sad way of doing things. This guy may say that. Maybe, okay, maybe, okay. But that's where we are, okay. It was sad. It was sad. It was sad. Now it's very sad, okay. Depends how you feel, okay? Depends how you feel. Okay. Now, so the nonlinearities control the correction to Higgs couplings. So there's an interesting connection here. Measuring Higgs coupling is the same thing as measuring fine-tuning, essentially. Okay, it's called fine-tuning theorem. You see it in Technicolor. Technicolor is the most natural theory. There's no Higgs. Deviations from standard model are order 1. The Higgs is not there, okay? And the more the Higgs looks like the standard model, the more, if you want to reproduce that in a theory, which aims at being natural, the more tuned it is. And then there is the search of resonances. Now, of course, the indirect searches, the EFT, all this measuring, coupling, it's the thing that takes a lot of attention, but actually it turns out that direct searches are more important at the end in terms of testing. Okay, the search for the top partners, okay, gives you constraints that are in the same range from the point of view of tuning, but the search for the vector resonances are give stronger constraints. Of course, we don't have a real theory, okay? These are qualitative constraints, but the present constraint on the vector resonances, for instance, in the model that you realize holographically, are already telling us that unless something unexpected happens, theories of composite Higgs, the correction to Higgs couplings are less than 1%, and unlikely to be seen at high Lumi LHC. Per contre, high Lumi LHC may be interesting for flavor. Let me get back to flavor. Okay. So flavor, as I said, you can explain masses like that. However, whenever at low scale you have a theory of flavor, you're almost always dead, okay? And if this theory explains things, explaining flavor means dying if you're doing it low energy, okay? Because if you explain flavor, it means that the sources of your theory are not the Yukawas of the standard model. There are other sources. And these other sources will violate G, okay? And this is what you have here, okay? Epsilon K, the EDM of the electron, you get these absurd scales, okay? If this is the situation, we will not see anything, not even at the LHC, but even at the FCC, okay? Why did I tell you this? Well, I told you this just to give you an idea of how hard it is to build models, okay? I mean, and flavor remains, in my opinion, the biggest stumbling block, okay? And however, it's also an opportunity, okay, as soon as you try to make the theories work, okay? So now the question is, so this is not appreciated, okay? There was a talk given by Andreas Höker at CERN. He was talking about the composite Higgs, and he didn't know this fact that flavor is generically so much stronger. And he was told, oh, but you can put flavor symmetries, and then if you have flavor symmetries, you are safe. Actually, it's more complicated than that. And to work that out in detail, so this was, so then what do you do? So if you want to have a composite Higgs that can be seen at present and future collider, then you have to give up the explanation of flavor, okay? You have to give up, and you have to come in with something that I abhor, in a sense, but you have to do it if you want to have physics at low energy, flavor NCP symmetries, okay? And, Michele, Riccardo, and collaborators have worked out examples of that in 10, 15 years ago. But it was a general analysis classifying service work, classifying all the possibilities, and their present and future implication was lacking. And so when I was doing when I was working for the European strategy in 2019, I thought this was necessary. Of course, it turns out that people don't care so much. And after 5 years, we came up with this 100-page paper where we classified essentially the classes of situations that you can foresee. Of course, you have infinitely many situations you can think, right? You can take any subgroup of SU3 to the fifth, and depending on how you break it, but then the question how you classify all the possibilities based on the phenomenology and their implications. And we got this 5. And let me give you an idea of what you get, okay? This is a set of plots in 2 classes of models of the situation right now and the situation what it will be in 15 years, okay, at least the reach, okay, the exclusion ability, in particular with the data from LHC-B and Bell, okay, in terms of flavor. The first interesting thing is that as soon as you add symmetries in order to bring the physics down, the main constraints go from being EDM of the electron and epsilon K, it comes from B physics mostly, okay? So B physics is the playground of theories with flavor symmetries, okay? And now on this plot, so this is this situation with maximal symmetry, the one that is unfortunately called minimal flavor violation or maximal flavor conservation. So these are the exclusions from Higgs couplings, electroweak tests, and some Drell-Yan production below threshold. This is the production of vector resonances. Okay, you have to live on this side. And these are the constraints from flavor. So BS to mu plus mu minus, BB bar oscillations. There's also some contact interaction that are flavor preserving that are associated with flavor, but they're flavor preserving. Okay, I don't want to get into the details of that. This is just to show you that when you make a model and you think of flavor, you cannot think just of flavor physics. There's no such thing as a flavor phenomenologist, okay? To do flavor physics, you have to couple it to other assumptions. If you're only a flavor phenomenologist, you will never see the interaction between these constraints, okay? And together, they become stronger. So then you can make further hypotheses, the thing becomes weaker. But you see, they're always stronger than the other constraints. So in the sense, even in the models with the highest symmetry, flavor wins. And in fact, in the next years, it will even explore regions that we were hoping to explore at FCCHH. Well, you may look at this in two ways. You can say, well, if this is the way we go, we may get a hint in the next 10, 15 years. 5 minuti, okay. This is actually optimal models that have less symmetry. And if you combine, again, this is the cleverness of model building. You add some left-right symmetry, you say some effects for some dynamical reason come at loop rather than tree. This is the region where flavor puts you now, and the bounds are weaker than the direct searches. This is almost a unique situation. But if not, then flavor wins. And even in this dark green situation, the next 15 years, flavor will essentially win or become comparable. Okay? So flavor is the future. Now, why did I went through that story about how you have flavor opportunities with new physics at the weak scale, if then it doesn't work? Well, because actually there is a way to make it work, okay? If you do anathema, if you put together compositeness and supersymmetry, okay? And I don't want to get into the details of that. Again, you have to run the risk of making a fool of yourself. You have to build models. But I wish we built models more often to get an idea of what we're doing. You may discover that you're doing crap, but if you don't try it, you and everybody else won't know. Anyway, this is the structure, okay? It's a bit articulated. Again, you can realize it holographically. Does a CFT that does that? I don't know, okay? Anyway, this is a supersymmetric composite X. There were timid or partial studies in the years when the LHC started, but then people stopped, okay? And actually, I think there is an opportunity here that was, to me, missed, okay? And this is where I'm studying with these friends. They should be coming up soon. You have a concrete case where gauge mediation matters. You have a concrete situation where the origin of the Higgs parameters in gauge mediation, which was always a nagging thing, here is not as nagging. I'm not saying that it's super beautiful, but it's not as nagging in the gauge mediation that we were building without trying to address also flavor. So if you put the things together, you have. And the nice thing, interesting thing, is that precisely asking that all the soft parameters are comparable, this sets the scale of compositeness here. Now, let me get back. How can I get back here? Now, this theory, well, okay, let me tell you. This is the scale of compositeness. Okay, the scale now can be high because naturalness is controlled by these particles. Okay, again, Strumia will tell you, okay, this is very tuned because we already know these particles are not there. Yeah, it's true, it's going to be tuned, maybe 1 in 100, maybe 1 in 1,000. I only had 2 flat tires driving in my life. I think I've driven millions of kilometers. One was in Texas, that's the bulk, okay? That everywhere in Texas, you can have, occupies the whole surface of Earth, you can have a flat tire. The other flat tire was exactly in the middle of the Mont Blanc tunnel under the signal Italy-France. Okay, you can say there's a look elsewhere effect. I don't care, it's me, it happened to me, okay? So it's the only person that matters to me, okay? So, maybe that's, go ahead. Okay, so yeah, we have to live with that, but tunings may exist, okay? 10 to the minus 2, 10 to the minus 3, we don't know, but that's precisely what we would like to know. If we found that the tuning has to be 10 to the minus 4, well, that's interesting, okay? That's what nature is. Now, another interesting thing, and this is for experiments, okay? Now, of course, in this scenario, the constraints for flavor are not killing you, but the biggest constraint, it's always the same. It's the EDM of the electron. This little David that can kill the Goliath, okay? The EDM of the electron, and why is that? Because the EDM of the electron the constraints have grown, have become very strong. They've grown by 3 orders of magnitude, actually almost 4 in the last 30 years. And for instance, David DeMille, so this is the present situation, okay? This is the present bound, and if you have the scale on composite 100 TeV and SUSY at the TeV, you're right there, okay? But this constraint, it's claimed by the people who work in this area, which is a beautiful little area of fundamental physics. A factor 20 improvement by ACME 3 is totally, they say it, we can do it, we will do it in the next less than 5 years, okay? So it's less than, and notice that, for instance, increasing by 2 orders of magnitude here amounts to increasing by 1 order of magnitude in the composite scale and 1 order of magnitude in the SUSY scale, means going to composite as 1,000 TeV and particle mass at 10 TeV, which is already out of essentially FCC. Okay? So the EDM of the electron, to me, is one of the most interesting ongoing experiments in fundamental physics. And with changes in the techniques, this is David DeMille who was telling me, there's the possibility, okay, with some R&D, to go beyond 10 to the minus 31, 32, maybe even 33, okay? It's very interesting. This is going to happen way before the FCC EE goes on, okay? So it could be that all this is futile in 10 years. Well, I'm finished, right? Okay, so I just want to tell you, if you want to know while we have lunch, the irresistible fascination of the Higgs trilinear, which is something that I can tell you any bad things about, okay? All bad things about. It's totally unmotivated, okay? If you want, we can discuss. But it's truly presented often as the flagship measurement of future machines. We should learn, I think, when we make these statements, to have some backup knowledge of what we are saying. And this is slipping from our hands. There's something else I wanted to say about the strong CP problem. There is this thing, could be a red herring, probably it's a red herring, even though these are very smart people. This is motivating work. Try to understand under what conditions can the QCD parameter run and you can compute it, okay? And there are some, we believe there are cases where you can really do a computation, okay? Really, you can do a computation. Anyway, this is again showing to you that quantum field theory and phenomenology are really fertile grounds for having ideas and exploring them, okay? So that's it. I think these are, to me, questions that are still there. They're evergreens, no matter what our friend here thinks or says. But the crucial thing, and let me insist, is that we have to make hypotheses, okay? Hypotheses are what we need, and I see it in the activity of phenomenologists, not the phenomenologists that are not QCD phenomenologists, the phenomenologists that supposedly have to do this jester job of explaining what we're doing is no longer done, okay? So we only work on we have this generalistic approach or this math approach. We really don't know what we are doing there. So if we want to discuss more on how to do this, certainly we can meet here, okay? This is the right place to meet. So long live to the GGI. Thank you for
Thank you, Riccardo, for this nice and inspiring talk. Questions before lunch? The other Riccardo.
Well, I mean, you did not discuss simple supersymmetry because it does not address flavor. Is that the point?
Yeah, I wanted to see a situation where you can address it at a low scale. Yeah, I wanted to address flavor in a way that we may be able to see it, not maybe in our lifetime, but in the lifetime of our grandchildren. Okay. So, okay, it doesn't have to be like that. Okay, flavor could come from string theory, could be worked out by Costas and Massimo if they only wanted. Okay.
But the problem is that you put everything to explain nothing. Now there is nothing at Large Hadron Collider, nothing in flavor, and you put supersymmetry, composite. At this point, you can drag the ether, and it's the same approach.
Yes. 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 Other question. No, very good, very good. Okay. So there is some interesting, for instance, in the last one that I presented, there's clearly an interesting and dangerous thing that is the light gravitino.
But beside that, I think if you eat up all these states, you will have a lot of, there is a high risk of overclosure, I would say.
Why?
Well,
which states?
Use a lot of gravitinos, you will produce...
No, okay. The gravitino in this range is light, so it's not playing a role for dark matter. Okay, in the low range of the model, okay, in the nice range of the model, the gravitino has a mass which is right at the edge, EV, of the present constraint from large structure. Okay, so it's at the edge, and it's around there. Yeah, it's light enough. Okay, it's light. It's warm dark matter. The gravitino, it's a fraction of, it's a sizable fraction of warm dark matter, and present constraints are heating it close, but not yet. So again, this is another thing that within the next 10, 15 years. Oh, yeah, I agree. I didn't say it, but this is important. Yeah, this is in fact something to study in more detail, yeah. Yeah, there are many ways in this can be dead in 10 years. Of course, yeah.
Okay, I don't see other questions, so let's thank again Riccardo. Before closing, let me thank all the speakers of both days and all the participants for this very nice workshop. Now we can go to lunch.